What if the grand narrative of our cosmic origins, our most profound story, might not be the true account? The James Webb Space Telescope, the world's most powerful cosmic observatory, was not built merely to capture beautiful images. Its primary mission was one of confirmation, to validate our established ideas about the Big Bang, time, and the dawn of existence. Yet, what this observatory has uncovered has shaken our understanding of the universe. We are now confronted with galaxies that should not be present, stars forming with impossible speed, and cosmic structures far too orderly to align with our theories. This growing body of evidence suggests we may have been following a flawed origin story all along. The implications go beyond scientific adjustment, potentially reshaping our entire conception of reality. It is the story of a telescope altering our perspective on everything. For decades, scientists have peered deeper into the cosmos, searching for the universe's primordial light, a faint signal from the dawn of creation. The prevailing explanation, the Big Bang theory, held that all of existence began 13.8 billion years ago, expanding rapidly from an infinitesimal point known as a singularity. Everything that followed, stars, galaxies, and life itself, was a consequence of that initial outward rush. Powerful observatories like the Hubble Space Telescope provided images that seemed to corroborate this narrative, showing an expanding universe and reinforcing many of our core beliefs. Then, the James Webb Space Telescope arrived. Known as JWST, it was not engineered to simply refine minor details of the existing model. It was conceived to gaze further back in time than any instrument before it. The goal was to capture the faint radiance of the very first galaxies and to witness the cosmic dawn, that pivotal moment when the first stars ignited and illuminated the primordial darkness. Its development spanned decades, cost nearly $10 billion, and resulted in the most powerful space observatory ever constructed. Launched in December 2021, Webb promised to open a new chapter in our cosmic story. Few predicted it might instead force us to close a chapter we thought was settled. From the moment JWST's initial images were released, experts knew they were witnessing something that defied expectations. The images were undeniably stunning, but concealed within the splendor of nascent galaxies were profound puzzles, contradictions, and structures that seemed shockingly mature. These were not the chaotic, infant galaxies predicted by Big Bang models. Instead, they appeared too large, too well-formed, and in some cases, too ancient. From our vantage point, they seemed like cosmic anomalies with no place in the early universe. The most startling detail was not just what Webb observed, but when. According to current cosmological models, the first galaxies should have required hundreds of millions of years to coalesce after the Big Bang. Webb, however, discovered fully formed galaxies that existed a mere 200 to 300 million years after that presumed beginning. Furthermore, these were not faint, tentative structures. They were massive, dynamic, and teeming with stars and heavier elements, features that established theories suggested should not exist so early. As more data arrived, a distinct pattern solidified: too many galaxies, appearing too soon, and they were too massive and too organized. This was not a minor issue to be resolved by adjusting a few parameters or adding a footnote to the standard model. It represented a discrepancy that questions the core assumptions of our entire cosmological framework. One astrophysicist stated bluntly that such galaxies should not exist. Another drew an analogy, comparing the discovery to expecting a classroom of toddlers but finding fully grown adults. These were not the hallmarks of a young, turbulent universe just beginning to take shape. They were the signs of a cosmos that seemed mature almost from its inception. This prompts a difficult question. What did we miss? Could our understanding of redshift, the stretching of light that indicates cosmic distance, be incomplete? Does cosmic time behave in ways we do not comprehend? Or could the very concept of a universe originating from a single, explosive event be simply incorrect? The ramifications are profound. The consistent data from James Webb, revealing early complexity where none was predicted, could prove a serious challenge to the Big Bang theory. This may require not just modifications, but a full replacement. This does not necessarily negate the idea of a cosmic beginning, but it strongly suggests the nature of that beginning. The when, how, and why was profoundly different than we imagined. Some scientists have begun to quietly consider the unthinkable. Perhaps there was no Big Bang at all. What if the universe did not burst into being? What if it has, in some form, always existed? Or perhaps it is part of an eternal cycle of expansion, contraction, and rebirth, operating on principles we are just beginning to contemplate. There is no question that the James Webb Telescope has already changed our view of the cosmos. It has done this not by disproving the Big Bang, but by delivering unexpected data, the hallmark of great science. When established opinion collides with direct observation, only one can prevail. The universe is indifferent to our expectations. It simply is what it is. Thanks to Webb, we now see that reality with more clarity than ever before. It is important to understand what the James Webb Space Telescope was built to see. It is not an upgraded Hubble, but a different class of instrument built for questions Hubble could never reach. While Hubble primarily observed light in the visible and ultraviolet portions of the spectrum, James Webb was specifically designed to see in the infrared. The reason for this infrared focus is simple yet profound. As the universe expands, the light emitted from the most ancient galaxies is stretched, shifting it toward longer, redder wavelengths in a process known as redshift. To witness the formation of the first galaxies, stars, and structure itself, one must look into the cool afterglow of the distant past. Webb provides precisely this capability. It orbits nearly 1 million miles from Earth at the gravitational stability point L2. There, it remains in the cold, dark shadow of our planet and its moon, protected from the sun's heat by a 5-layer shield the size of a tennis court. This allows it to operate in near total darkness, detecting faint traces of infrared light that have journeyed for over 13 billion years. By its very design, it is a time machine, not metaphorically, but literally. The deeper Webb peers into space, the older the light it intercepts. But it was built not just to see far, but to see first. A central mission was to detect the very first stars and galaxies, a period in cosmic history called the Cosmic Dawn. This was the era that followed the so-called Dark Ages, a time after the Big Bang when matter had cooled enough for atoms to form, but before stars had ignited to pierce the darkness. Researchers had anticipated that the Webb telescope would find the earliest glimmers of starlight, marking the universe's fundamental shift from cold, dark clouds of hydrogen to hot, luminous structures. The prevailing models suggested it would capture nascent galaxies coalescing in chaotic clusters, their stars composed almost exclusively of hydrogen and helium with very few metals. In essence, Webb was engineered to provide a more detailed confirmation of the Big Bang's aftermath, revealing the universe's first light with unprecedented clarity. The telescope was also constructed to address other persistent questions, such as how galaxies evolve over time, how stars are born within immense clouds of gas and dust, and whether we could analyze the atmospheres of distant exoplanets. Webb's enormous 6.5 meter gold-coated mirror, with a diameter more than 2.5 times that of Hubble's, was specifically designed to resolve these cosmic enigmas. Its power lay not just in detecting faint, remote objects, but in unveiling their structure and detail in a way no previous instrument could. The scientific mission was expansive. The expectation was that by looking far enough back in time, astronomers would witness the primordial chaos predicted by the Big Bang model, infant galaxies just beginning to assemble with simple structures and irregular shapes. They hoped to observe the gradual emergence of complexity over eons, a process that would support the established timeline where stars slowly forged heavier elements and galaxies grew through mergers over billions of years. What the telescope actually saw, however, was something else entirely. While the initial images Webb sent back were celebrated for their sheer beauty, it was the underlying data that created tremors throughout the scientific community. Instead of disordered, infant galaxies, Webb discovered massive, well-organized systems that existed astonishingly close to the supposed beginning of time. In place of the expected metal-poor stars, it found objects rich with heavier elements that, according to theory, should not have been present so early. Rather than observing galaxies being built slowly from cosmic dust, we were looking at snapshots of what appeared to be fully mature structures, already in place when the universe was just a cosmic toddler. This was not a subtle issue of precision or a matter of interpretation. The observations were in direct conflict with what Webb was meant to confirm. The telescope performed its duties flawlessly. It peered back to the very edge of the observable cosmos, captured the faintest infrared light, and resolved galaxies never before seen. But in fulfilling its mission, it uncovered something unexpected. Our theories might not have been ready for the reality it revealed. We constructed the most advanced observatory in history to validate our best cosmological models, and it may have instead begun to unravel them. Every capability designed to reinforce our understanding of the Big Bang now seemed to introduce new questions. The timeline for cosmic evolution appeared to be compressed, the structures more developed than anticipated. The formation of stars and galaxies, a process once believed to require hundreds of millions of years, now seemed to have occurred almost instantaneously. Adding to the perplexity was the fact that Webb was operating exactly as designed. There were no discernible flaws in its systems or calibration. Its instruments were providing clear, comprehensive views from its perfectly aligned mirrors. The problem did not reside with the tools, it resided with the ideas. The James Webb Space Telescope was not just looking into space, it was looking into our own assumptions. And the light it gathered carried the disquieting suggestion that perhaps we were mistaken not about the data itself, but about its profound implications and what the Big Bang Theory truly describes. To fully appreciate how the James Webb Space Telescope could be shattering our cosmic worldview, it is necessary to understand the very model it is now challenging. The phrase Big Bang is used so frequently and in so many different contexts, from documentaries and pop culture to classrooms, that its scientific meaning is often diluted through oversimplification. The popular conception is of a singular, immense cosmic blast that hurled matter out into a pre-existing void. This image, however, is not quite accurate. The Big Bang was not an event that occurred in space. It was the expansion of space itself. The Big Bang Theory is, at its heart, a mathematical model of the universe's expansion. It posits that approximately 13.8 billion years ago, all of space, time, matter, and energy were concentrated into a state of unimaginable heat and density. This was not a point located within a larger emptiness, but rather space itself compressed to a nearly zero volume. From that state, space itself began to expand, not into anything, but as a stretching of the fabric of reality. This expansion continues today, with galaxies not flying through space, but being carried apart as the space between them grows. A strong body of evidence supports this model. In 1929, the astronomer Edwin Hubble provided one of the most famous pieces of evidence when he observed that light from distant galaxies was redshifted, meaning it was stretched to longer wavelengths. This indicated that they were moving away from us and that the universe was expanding. Tracing this expansion backward leads logically to a time when the universe was smaller, denser, and hotter, ultimately reaching a singularity, the mathematical essence of the Big Bang Theory. Over the following decades, more data reinforced the idea. In 1964, scientists accidentally discovered the cosmic microwave background radiation, or CMB. This is a faint, pervasive glow of microwave light that emanates from all directions in space and was identified as the cooled remnant of the hot, dense early universe, an afterglow that Big Bang proponents had predicted years before. Later, precise measurements were taken of the abundance of light elements like hydrogen, helium, and lithium. The quantities found in the cosmos closely matched the amounts predicted to have been formed through nuclear fusion in the first moments of a hot, rapidly expanding universe. All of these findings converged to create a remarkably successful framework, a universe born in a fiery state, expanding and cooling ever since, and gradually forming stars, galaxies, and eventually, life. The model worked so well that it became the standard cosmology, integrated into textbooks, simulations, and the global scientific consensus. But despite this success, there were always unresolved gaps. One of these was the horizon problem, which questions why the universe appears so uniform when different regions should never have had time to exchange energy or information. Another was the flatness problem, which asks why the universe's geometry is so close to being perfectly flat. The monopole problem raised the question of why we do not observe traces of high-energy particles that should have been created if the universe began as our theories suggest. To resolve these issues, cosmologists in the 1980s proposed a refinement called cosmic inflation. This idea held that in the first tiny fraction of a second following the Big Bang, the universe expanded exponentially at a rate faster than the speed of light. This inflationary event is thought to have smoothed out primordial inconsistencies, stretching the fabric of the universe until it was exceptionally flat and diluting any exotic relics from the earliest moments. This concept became a crucial addition to the Standard Model. It was not part of the initial Big Bang theory, but today it is inseparable from most contemporary versions. As a result, when scientists now refer to the Big Bang, they are usually describing a composite framework. The narrative begins with an initial singularity, followed by an explosive burst of inflation, which then transitions into a more measured, slower expansion. As the universe continued to cool, hydrogen and helium formed, the cosmic microwave background was released, and finally, the first structures began to take shape. It is important to recognize that the Big Bang theory does not attempt to explain the universe's origin or what might have existed before it. Indeed, the traditional perspective holds that time itself originated with the Big Bang, meaning there is no before. The theory also offers little insight into the true nature of the singularity, as this is the point where our mathematical models fail. At such extremes, quantum effects become dominant, and general relativity no longer has predictive power. This is the context in which the James Webb findings are so profoundly unsettling. The established theory predicts a slow, methodical emergence of structure from an initially chaotic state. Galaxies should assemble over vast periods. Stars are expected to evolve through known fusion pathways, and the entire sequence of events should conform to the timeline established by the cosmic microwave background and redshift measurements. But if the Webb telescope is observing galaxies that seem too old, too large, and too orderly for their early cosmic epoch, then that entire timeline may be incorrect. And if the timeline is flawed, the fundamental principles that link redshift, distance, and age could also be in error. This would suggest that our calculations of the universe's age, or even the rate of its expansion, might be wrong. More unsettling still, it could mean that what we believe we know about space, time, and light is incomplete, which would leave our entire model of the cosmos on shaky ground. Well before the James Webb Space Telescope delivered its astonishing images, there were already hints that galaxies were not behaving as expected. These early clues emerged from the Hubble Deep Field, one of the most famous collections of images ever captured. An observation that started as a risky gamble ultimately became a new way of looking into the distant past. In 1995, astronomers aimed the Hubble Space Telescope at what appeared to be a completely barren patch of the sky, a region devoid of stars, galaxies, or any other obvious targets, just darkness. They held the telescope's shutter open for 10 consecutive days. What they discovered left everyone stunned. The image revealed thousands of galaxies, densely packed into a space that had seemed empty. Each faint smudge, each delicate spiral or blurred arc was a galaxy, with some situated over 10 billion light-years from Earth. This meant we were observing them as they appeared near the dawn of time. This single image transformed astronomy. It demonstrated that the universe contained far more galaxies than previously imagined. The observation validated the idea that by peering deeper into space, we could witness progressively earlier stages of cosmic evolution. Over the following years, Hubble would repeat this technique multiple times, creating the ultra-deep field and the extreme deep field, each pushing closer to the theoretical limits of observation. Yet, as the image resolution improved and more redshift data was gathered, a strange pattern began to surface. Some of the galaxies within these deep field images seemed too developed for their apparent age. They displayed complex features like spiral arms, central bulges, and even indications of organized rotation. These were not the chaotic, irregular proto-galaxies that simulations of the early universe had led astronomers to expect. Instead, they looked like mature galaxies. According to redshift calculations, however, they existed only a few 100 million years after the Big Bang. At first, these were largely considered statistical outliers. Perhaps the galaxies were being misidentified, or their light might have been distorted by gravitational lensing. Another possibility was that they were simply flukes, a few unusual cases that did not undermine the overall model. But the sense of unease persisted. A growing number of studies pointed to the same conclusions. Galaxies were appearing too early, stars possessed unexpected metal content, and black holes were far too massive for their age. While the standard model remained the best explanation, it was accumulating challenges. The fundamental issue was a conflict with cosmic timelines. According to the Big Bang framework, gravity requires hundreds of millions of years to gather gas into stars, for those stars to complete their life cycles, and for their remnants to coalesce into more complex systems. Heavy elements, which astronomers refer to as metals, are forged in the cores of stars and dispersed by supernovae. Consequently, the early universe should have been metal-poor and structurally primitive, but some galaxies in the Hubble deep fields defied this expectation. They appeared chemically enriched, gravitationally stable, and rotationally organized. One of the most compelling examples came from a galaxy known as GNZ 11. First spotted by Hubble and later confirmed with spectroscopy, GNZ 11 appeared to exist just 400 million years after the Big Bang. Despite its youth, it was as massive as 1 billion suns and exhibited signs of star formation at a rate that should have been impossible at that stage. It was not merely surviving, it was thriving. Still, astronomers exercised caution. Hubble's capabilities, though revolutionary, had their limits. The deeper it peered, the more difficult it became to distinguish faint galaxies from background noise. Furthermore, its sensitivity to infrared light, which is essential for detecting highly redshifted objects, was not its greatest strength. What was truly needed was a telescope that could see deeper and with greater precision, one with an instrument suite specifically tuned for the cool, stretched light of the early universe. That telescope would be the James Webb. What is critical to appreciate, however, is that Webb's most startling discoveries did not arise in a vacuum. The seeds of the current cosmological crisis were already present in those deep field images. The signs were there: galaxies evolving too quickly, stars forming in unexpected environments, and mass accumulating faster than any existing model could predict. The way science confronts these kinds of discrepancies is what makes this moment so powerful. Initially, the data is met with skepticism. Then it is scrutinized, challenged, and often assimilated into existing theories. But at a certain point, when the anomalies accumulate and can no longer be explained away, science itself must change. What began as a few peculiar galaxies in a deep field photograph may now be recognized as the first cracks in the foundation of the Big Bang model. The James Webb Space Telescope has not only captured breathtaking images of the cosmos, it has also illuminated a profound problem in our understanding of cosmic time, revealing too many mature galaxies far too soon. The prevailing view held that galaxies would assemble gradually over billions of years, a slow process governed by gravity and atomic chemistry. What the James Webb Space Telescope revealed, however, was something entirely different. A population of galaxies that were already massive, organized, and seemingly ancient, existing only a few 100 million years after the Big Bang. This was not a case of one or two outliers. There were simply too many of them to be dismissed. Within weeks of the telescope's first deep field observations being released, astronomers began to recognize a pattern they had not foreseen. What emerged was a census of galaxies so large and well-developed that it seemed to defy the established model. Scientists had anticipated finding small, irregularly shaped clouds of gas, tiny proto-galaxies in their earliest stages of coalescing. Instead, the images showed enormous systems. Some of these already possessed stellar masses comparable to our own Milky Way, yet they were flourishing just 300 to 400 million years after the universe's presumed beginning. According to the tenets of standard cosmology, this should not have been possible. The model requires an immense amount of time for atoms to even form after the Big Bang. More time is needed for gas clouds to collapse and ignite into stars, and still more for those stars to complete their life cycles, seeding space with heavier elements for subsequent stellar generations. Galaxies were not supposed to emerge fully formed at the dawn of cosmic history. They were expected to grow incrementally, sculpted over eons by mergers, bursts of star formation, and complex feedback mechanisms. But the Webb telescope unfurled a cosmos that looked less like a construction site and more like a finished showroom, with everything polished and in place far ahead of schedule. A team of researchers led by Dr. Gian Cartali conducted one of the initial analyses that caused widespread concern. Examining the early science data from JWST, they identified dozens of luminous, massive galaxies at redshifts greater than 10. This corresponds to a period when the universe was less than 500 million years old. Despite their youth, these galaxies exhibited signs of being not only immense, but also chemically mature and structurally complex. Their shapes included features like rings, central bulges, and possibly even the beginnings of twisting arms. They had the appearance of seasoned veterans from a later cosmic era, not newborn structures in a primordial universe. This finding was more than just a surprise. It presented a direct challenge to the mathematical framework supporting the Big Bang model. To form galaxies of such a scale so quickly would necessitate either star formation rates far exceeding expectations, undiscovered mechanisms of mass accumulation, or a fundamental revision of the timeline of the early cosmos. The calculations simply did not align with the observations. The rate at which matter could gravitationally clump, form stars, and organize into galactic structures was insufficient to explain the sheer volume of galaxies that Webb was detecting in such a short time frame. Some astronomers attempted to reconcile the data by adjusting models of star formation, proposing that perhaps these early galaxies were just exceptionally efficient at creating stars. This explanation, however, encountered its own logical hurdle. The more efficiently stars form, the more intense radiation and stellar feedback they produce, a process that should theoretically slow down or halt further star formation, not accelerate it. Another suggestion was that the galaxies were being misidentified, or that their redshift measurements were inaccurate. Yet, subsequent spectroscopic confirmations solidified the initial findings, verifying that these galaxies were indeed as ancient and as massive as they first appeared. What truly compelled cosmologists to reevaluate their assumptions was the staggering number of these fully developed galaxies. A single anomaly might be explained away, but Webb's observations revealed a consistent population, a statistical reality that could not be overlooked. The early universe was not only more orderly than previously thought, but it was also populated with an abundance of large structures. This raised profound questions about our very understanding of cosmic time. If galaxies were forming too rapidly, could it be that time itself behaved differently in the early universe? Or perhaps the relationship between redshift, distance, and age is not as straightforward as current models presume. If that were the case, a foundational pillar of observational cosmology, the very method we use to date distant objects, might require a complete reassessment. The problem deepens when considering the implications for cosmic evolution. If galaxies did not require billions of years to mature, what would that reveal about our understanding of structure formation, the dynamics of dark matter, and the role of feedback processes? It is akin to discovering a modern city in the fossil record of the Jurassic period. It indicates a fundamental error in the established timeline of events. For decades, the Big Bang theory has served as more than just a scientific framework. It has been a grand narrative of creation, told through mathematics and light. It offered a story that progressed from primordial simplicity to intricate complexity, from a hot plasma to the emergence of humanity. But the data from Webb has cast doubt on the pacing of that story. It could be that the script is correct, but the timing is profoundly off. Or, in a more radical interpretation, the entire story we have been telling ourselves is either incomplete or fundamentally mistaken, and this is merely the beginning of the investigation. In the years to come, the James Webb Space Telescope will continue to study these early galaxies in greater detail. Improved spectroscopy, more refined imaging, and deeper surveys will either resolve these anomalies or see them multiply. In either scenario, the scientific tension is mounting, fueled by galaxies that are too large, too mature, and formed too quickly. Astronomers had anticipated that the first deep-field images from the James Webb Space Telescope would reveal small, chaotic galaxies. These were meant to be the initial blueprints for the elegant spiral and massive elliptical galaxies that would form later. What they discovered instead was something that should not have existed: galaxies that appeared fully realized, large, old, and moving with purpose. These were not isolated flukes or observational errors. They were a consistent feature across Webb's field of view, and they stood in direct opposition to the conventional narrative of cosmic history. In our current model of the universe, there is a prescribed rhythm to cosmic formation. Galaxies are thought to begin as small concentrations of matter in the infant cosmos, growing progressively over billions of years through a series of mergers. gravitational accumulation, and episodes of intense starbirth. This hierarchical model, where smaller structures combine to form larger ones, is a core concept within Big Bang cosmology. Yet Webb has found galaxies that appear to have bypassed this entire process, emerging as massive and complex systems far too early in the cosmic timeline. One galaxy in particular, Sears 1749, is estimated to have existed just 500 to 600 million years after the Big Bang. Its mass, however, seems to rival that of the Milky Way, a galactic system that took more than 13 billion years to reach its current state. The central question is how something so enormous could already be in place when, according to existing models, there simply had not been enough time for that much structure to assemble. The data indicated that these galaxies were not merely present, they were active and thriving. Some were creating stars at rates 10 to 20 times higher than models predicted for that era. Others displayed evidence of ordered rotation and distinct galactic disks, features that are thought to require significant time, mass, and gravitational stability to develop. It was not just their immense size that was so puzzling, it was their surprising level of maturity that truly captured the attention of the scientific community. What was most startling was the age of these galaxies, or rather, what their maturity suggested about the passage of time in the nascent universe. The observation that they were already fully formed at such high redshifts indicated that their stars must have ignited even earlier, potentially within the first 100 to 200 million years of cosmic existence. This is a profoundly short period for all the required steps of gas cooling, gravitational collapse, star formation, and the organization of a galactic structure. It is a timeline far more compressed than what the Big Bang model would ordinarily accommodate. Another area of concern involves velocity, specifically how rapidly these galaxies were manufacturing stars and accumulating mass. The observed rates of star formation were frequently so extreme that they surpassed a theoretical boundary known as the Eddington limit. This limit defines the maximum possible speed at which matter can accrete onto an object before the outward force of radiation pressure blows it away. These galaxies were not only growing with incredible speed, but they were doing so at a pace that challenged the very limits of what astrophysics considers possible. These three factors, being too large, too ancient, and too fast, converge to create a significant contradiction. It is not a matter of simply explaining away a single anomaly. To make the observations align with theory, one would need to introduce numerous adjustments to the conventional model, and even then, a considerable tension would likely remain. The challenge to the Big Bang model intensifies with every new, unexpectedly massive early galaxy that the Webb telescope discovers. In an effort to reconcile the data, some scientists have proposed that primordial galaxies might have been more efficient than their modern counterparts, perhaps by consuming their reservoirs of gas more quickly. Yet this idea merely postpones the fundamental question: how could such a high level of efficiency emerge so rapidly, in such great numbers, and across such vast regions of the early cosmos? It also fails to explain why our models did not foresee this outcome. An alternative hypothesis suggested that denser clumps of dark matter in the young universe might have formed exceptionally deep gravitational wells, which would allow ordinary matter to collapse more swiftly than anticipated. However, even this modification struggles to account for the sheer quantity of massive galaxies that Webb has identified. Furthermore, it does not address the advanced metallicity and organized structures observed in so many of them. If the timeline for galaxy formation is indeed incorrect, it could imply that our methods for measuring cosmic distances, which rely heavily on redshift, require re-evaluation. It might also suggest that time itself functioned differently in the early universe, or that our entire model of cosmic expansion needs a fundamental update. A more radical notion is that the physical laws we observe today may not have applied in precisely the same way when the universe was in its infancy. These profound questions are now propagating through the field of astrophysics like shockwaves. The standard model of cosmology, known as LCDM, which stands for Lambda Cold Dark Matter, has long been regarded as exceptionally robust. It successfully explains cosmic expansion, the cosmic microwave background, the large-scale structure of the universe, and much more. But the findings from the James Webb Space Telescope are now probing the very boundaries of that confidence. Some researchers have gone so far as to describe the initial results as a crisis in cosmology, one that necessitates either substantial revisions or a completely new interpretation. All the while, the Webb telescope continues its mission, steadily delivering more data. Each new image and every deeper exposure seems to unveil yet another galaxy that is too massive, too developed, or forming too quickly to fit the established timeline. And as scientists work diligently to refine their measurements and explore alternative theories, the broader picture becomes increasingly difficult to dismiss. The early universe appears less like a gradual construction zone and far more like a pre-existing cosmic metropolis. It remains too early to determine if these discoveries will lead to a complete overthrow of the Big Bang theory. Scientific paradigms are not abandoned overnight, but history teaches us that when observation consistently conflicts with theory, the responsibility falls on the theory to adapt. The concept of redshift is one of the most foundational pillars of modern astronomy. It is the tool that informs us of an object's distance in the cosmos, which in turn allows us to map out cosmic time. It is the very measurement that tells us how far away a galaxy is and, consequently, how far back in time we are observing it. But in light of the new discoveries from the James Webb Telescope, a number of scientists have begun to ask a difficult question. What if we have misinterpreted redshift? To grasp the significance of this inquiry, it is essential to first understand what redshift is believed to represent. As light journeys from a distant source through the expanding fabric of space-time, its waves are stretched. This phenomenon is analogous to how the pitch of a receding ambulance siren deepens. The wavelength of light increases as its source moves away from an observer. Blue light shifts toward the red end of the spectrum, giving the effect its name. Within cosmology, redshift serves as a primary gauge of cosmic expansion. A higher redshift value corresponds to a greater distance and, critically, a view deeper into the past. An object with a redshift of 2 is seen as it was when the universe was approximately 3 billion years old. An object at a redshift of 10 is from a time when the universe was less than 500 million years old. The greater the redshift, the nearer we are to the moment of the Big Bang. This relationship is the basis upon which we have constructed the entire cosmic timeline, from the birth of the first stars and galaxies to the emergence of black holes and even the rate of the universe's expansion. Redshift, in this sense, is not merely a measurement, it is the structural backbone of our cosmic history. The issue is that the galaxies being seen at extreme redshifts with values of 10, 11, 12, and even higher are not behaving as this timeline would predict. They appear too large, too evolved, and too structured, as if they were afforded much more time to develop than the standard model allows. One possible explanation is that these galaxies are in some way deceptive, that their brightness, mass, or structure is misleading us about their true age. But there is another, more profound possibility, that our interpretation of redshift itself is incomplete. Could it be that redshift is not conveying the information we have long assumed it does? Perhaps cosmic expansion is not the sole, or even the primary, reason why light becomes stretched over immense cosmic distances. This is not a new line of questioning. In fact, it touches upon one of the longest-standing controversies in the history of cosmology. When Edwin Hubble first observed in the early 1900s that galaxies were redshifted and appeared to be receding from us, some physicists proposed alternative explanations for this phenomenon. The tired light theory was among the most prominent of these alternatives. This hypothesis suggested that photons gradually lose energy as they interact with particles or fields while traversing the vastness of space, causing them to become redder. In that framework, redshift would be an indicator of distance and the fatigue of light, not evidence of an expanding universe. That particular theory eventually fell out of favor due to a lack of supporting evidence and its inability to align with certain key observations, such as the precise spectrum of the cosmic microwave background. Nevertheless, the discoveries from Webb are breathing new life into these old questions. If expansion alone cannot adequately explain the unexpected maturity of high redshift galaxies, we are compelled to ask if some other process is influencing how we interpret the light from the distant universe. At a more abstract level, certain theoretical concepts are also beginning to challenge our interpretation of redshift. Some physicists propose that space-time itself might not be a perfectly uniform fabric, particularly during the universe's earliest moments. If the curvature of space-time or the effects of quantum fluctuations were more pronounced in the distant past, light traveling through it could have been redshifted in ways our current models do not account for. Other theories suggest that light might interact with dark matter or dark energy over cosmic timescales, subtly altering its frequency across billions of years. Still, another line of thought points to the possibility that light operates under different rules at the quantum level. This would mean redshift could be shaped by influences completely outside the standard model of physics. If the fabric of space is granular, if time is an emergent property, or if the speed of light itself has not been constant throughout cosmic history, then our entire framework for interpreting redshift may rest on a shifting foundation. There is also the disquieting acknowledgement that much of how we calibrate redshift relies on the very models now being called into question. We employ redshift to estimate distance, yet we also depend on models of galactic evolution to infer redshift. This form of circular reasoning becomes precarious when the James Webb data begins to challenge the very models used to interpret its findings. It is certainly premature to abandon the concept of redshift entirely. The idea continues to be one of the most reliable and predictive pillars of cosmology. However, the precision with which we equate redshift to cosmic time and distance might require a significant recalibration. It could be that redshift does signify expansion, but not in a simple, one-size-fits-all manner. It's also possible that in the universe's first epochs, some unknown phenomenon distorted the relationship we have long come to trust. Then there are the impossible stars. The James Webb Space Telescope was anticipated to observe the first stellar generation, known as Population 3 stars. These celestial bodies were theorized to be immense, hot, and composed almost exclusively of hydrogen and helium. They were expected to be the universe's inaugural light sources, born into a cosmos pristine and devoid of heavy elements. But instead of discovering these long-theorized primordial stars, Webb has revealed something entirely unexpected. It has found stars that should not exist so early, formed in a way that conflicts with the timing and chemistry of the standard cosmological model. What Webb observed were massive, luminous stars embedded within ancient galaxies. They radiated with incredible intensity, showing not just the signatures of hydrogen and helium, but also clear evidence of metallicity. In astrophysical terms, metals refer to any element heavier than helium, such as carbon, oxygen, nitrogen, and iron. All of these are forged deep inside stars and then scattered by supernova explosions. The presence of such elements in these early stars implies that several cycles of stellar birth and death must have already unfolded. Yet Webb is detecting these enriched stars only a few 100 million years after the supposed Big Bang. This leaves an astonishingly small window of time for multiple generations of stars to form, expire, and recycle their materials into more complex offspring. This sequence of events should not be happening. According to the Big Bang framework, the first stars emerge after cosmic recombination, when electrons and protons join to form neutral atoms. This event allowed the universe to cool sufficiently for gas to clump together under gravity. These Population 3 stars, if they existed, would have lived brief, violent lives, ending in brilliant supernovae. Their deaths would pave the way for second and third generation stars, enriched with those heavier elements. But this entire process requires time, hundreds of millions of years, if not longer, to build up the levels of metallicity we are now seeing in stars that appear far too soon. Webb's discovery of stars with high metallicity at such extreme redshifts poses a serious problem. It suggests not just early star formation, but an early chemical evolution at a speed and scale that current models cannot replicate. In galaxies like GNZ 11 and CERS 1019, the stars appear to be not only intensely hot, but also chemically complex. That complexity requires a stellar life cycle that should be impossible within such a short cosmic window. Some experts have tried to explain this by suggesting that star formation was simply hyper-efficient in the early universe. It is possible that conditions in the very first galaxies enabled stars to form, live, and die on a much accelerated timeline than was previously thought. They might have been denser, cooler, or had their chemical cycles jump-started by shock waves from collisions. But this idea struggles to be a logical fit, because Webb is not just finding one enriched star or galaxy, it is finding many of them. This common trend makes it seem as though the early universe was not a blank canvas waiting to be painted, but a scene already filled with detail. What is even more strange are the stars that are too large for existing theories to comprehend. Based on Webb's findings, some of these stars may have masses hundreds of times greater than our Sun, which could be near the theoretical upper bounds. The conventional view is that large stars are unstable, and that radiation pressure should break them apart or cause them to collapse into black holes. But in the early galaxies Webb examined, enormous stars seem not only possible, but also common. These impossible stars shine with such luminosity and complexity that it is hard to imagine them forming without some precursor conditions. Yet there should not have been enough time since the supposed origin of the universe for those conditions to exist. Even accounting for gravitational collapse and rapid cooling, the interval between the Big Bang and the formation of these stars is alarmingly short. What if the universe did not start with simple hydrogen clouds and a clean slate? What if, instead, the early universe was already chemically active, already building stars with metals, and already forming systems more advanced than we expected? That would suggest a very different origin, or at least a different pacing than the Big Bang theory allows. Some unconventional ideas, like plasma cosmology or steady-state models, propose that the universe is endless or cyclical. In these views, matter and energy are always changing instead of being created in a single event. These points of view suggest that early stars are not really early at all. They are just part of a process that happens over and over again in the universe. While these models have not been in the mainstream for some time, Webb's results are giving them some renewed attention. There is also the chance that our entire model of stellar evolution is missing a key component. Perhaps the physics of the early universe allowed for faster fusion, quicker lifespans, or exotic stellar behaviors we do not yet understand. Maybe dark matter played a catalytic role, or perhaps there is an unknown factor influencing how stars are born, live, and die. Until these observational gaps can be closed, we are left contemplating a cosmos that seems to be operating under a different logic than we expected. Stars that our models predicted should be impossible because of their immense mass, their great age, or their advanced chemical makeup are not only turning out to be real, but they appear to be numerous. Their presence is forcing us to revise the very narrative of how light first returned to the universe. We are also discovering ancient black holes where none were thought to exist. Many people imagine black holes as the final, destructive forces of the cosmos. They are either the dense, collapsed remnants of exceptionally massive stars, or the gargantuan monsters that reside in the hearts of galaxies. Their creation is not a straightforward or swift process. Within the standard astronomical model, black holes are considered a late-stage phenomenon. Their formation, life, and eventual death require the passage of stellar generations. Their growth depends on mass from mergers and a slow, often violent construction over eons. The James Webb Telescope, however, is finding them everywhere, appearing far too early in cosmic history and at far too great a size. Supermassive black holes, which can contain the mass of millions or even billions of our suns, are typically found in well-established, mature galaxies. Our own Milky Way contains one, Sagittarius A*, which sits quietly at our galactic center, a gravitational anchor that took billions of years to form. Yet Webb's observations are detecting active galactic nuclei, or AGN, the brilliant, energetic signatures of matter spiraling into black holes within galaxies that existed less than 700 million years after the Big Bang. Some of these black holes already seem to possess masses equivalent to hundreds of millions of suns, and that timeline presents a significant challenge. This is not a process that can happen quickly. It requires immense amounts of time. Even if you begin with a seed black hole, perhaps the remains of a very large population 3 star, weighing around 100 solar masses, it would still need to grow continuously through accretion and collisions with other galaxies to reach a supermassive state. The most optimistic models suggest this process needs hundreds of millions to billions of years to complete. Webb, in contrast, is seeing them fully formed before the universe had reached that age. This is not just evidence of early black hole formation, it points to early black hole dominance. Some of the host galaxies seem to be organized around these giants, which suggests that black holes may not have been a mere consequence of galaxy formation. Instead, they might have been a fundamental prerequisite. This possibility inverts the traditional model entirely. The galaxy known as CERS provides one of the most stunning examples. It is a living galaxy with a giant black hole that was already present when the universe was only about 570 million years old. What is even more remarkable is that it appears to be actively accreting matter, indicating it was not dormant, but was consuming gas and influencing its environment. This is the type of activity typically seen in galaxies that are much further along in their developmental journey. Some scientists have suggested that these black holes could have been created through direct collapse, an alternative pathway where immense clouds of gas fall in on themselves to form a black hole directly, bypassing the star phase altogether. This would produce larger seed black holes from the outset, enabling them to grow much faster. But even this theory has difficulty explaining how such seeds could be in place and already feeding so early, particularly inside galaxies that are also forming stars at a rapid pace. To achieve such quick growth, these early black holes needed more than just a starting mass. They required a plentiful supply of fuel. They would need cold gas, dust, and other matter falling into them at just the right velocity. But such a smooth and rapid feeding process contradicts many of our models, which predict that turbulence, feedback, and fragmentation would significantly slow things down. And yet, Webb is finding these behemoths already established and active, quietly defying every timeline we thought we understood. Even more confounding is the sheer quantity of these early supermassive black holes. They are not isolated curiosities. They seem to be a common feature in the first galaxies. This implies a universal mechanism at work, not a rare exception, which in turn suggests something much deeper may be incorrect about our foundational assumptions. If black holes of this scale existed so early, it changes our understanding of structure formation, star formation, and even reionization, the very process by which the first sources of light transformed the universe's opaque hydrogen fog into the transparent cosmos we see today. Through their intense radiation, black holes might have played a far more significant role in shaping the early universe than was previously believed. Some are even beginning to entertain the idea that black holes are not the endpoint of cosmic evolution, but perhaps the beginning. A few models now propose that primordial black holes, which would not have formed from stars but directly from quantum fluctuations in the nascent universe, could have been the very seeds that triggered the formation of galaxies. In this version of cosmic history, black holes did not wait for galaxies to form around them. Rather, it was around these primordial black holes that galaxies first began to coalesce. It is a deeply unsettling reversal of cause and effect, and it compels cosmologists to consider uncomfortable new possibilities. If supermassive black holes are this ancient, this common, and this integral to galactic life, then perhaps our universe did not evolve in the slow, linear way we had envisioned. Maybe it leaped into complexity faster than we ever thought possible, or perhaps that complexity was there from the very start. This leads to another area of inquiry: dark matter in crisis. For decades, dark matter has been the silent, invisible framework of the cosmos. It is the enigmatic substance believed to make up more than 80% of all matter in the universe, providing the gravitational glue that holds galaxies together. It does not emit, reflect, or interact with light or the electromagnetic force, but its gravitational influence is felt everywhere. At least, that is what we thought. The James Webb Space Telescope is now challenging this view. Webb's examination of the universe's most ancient galaxies and structures has not only raised questions about their age and size, but it has also begun to call into question the very framework that is supposed to hold them together. When we apply dark matter models to Webb's data, however, a troubling inconsistency emerges. The mathematics does not align with the observations. The standard cosmological model, known as lambda CDM, which stands for lambda cold dark matter, is built upon the idea that dark matter clumped together in the early universe. This clumping created deep gravitational wells into which ordinary matter could then fall. This process is what supposedly initiated the formation of galaxies, stars, and eventually planets. In this model, dark matter was not a passive background element. It was the first actor to take the cosmic stage. But Webb's observations now suggest that large, well-structured galaxies emerged far earlier than the lambda CDM model permits. If these galaxies possess dark matter halos, as the model requires, then those halos would have needed to form with extreme rapidity, more rapidly than the model allows. In other words, if dark matter was performing its designated role in the early universe, it was doing so far too efficiently and far too soon. On the other hand, a different narrative is emerging from Webb's observations of certain galaxies, which seem to exhibit a reduced reliance on dark matter compared to what has long been assumed. The spectral data that scientists analyze to determine mass distributions and rotational characteristics do not consistently align with the outcomes predicted by dark matter's influence. These distant galaxies behave as if they are held together by a smaller amount of this invisible substance than our standard models require. This is not the first instance where dark matter has presented a deep puzzle. Even within our local cosmic neighborhood, a few galaxies, such as NGC 1052 DF2, have been found to contain almost no dark matter at all, directly challenging established theories of galactic formation. Yet these were often seen as isolated, localized anomalies. What the Webb telescope is revealing is that the very earliest galaxies, which were thought to be shaped almost exclusively by dark matter, are not conforming to the expected behavior of systems governed by this mysterious component. The distribution of cosmic structure presents another area of significant tension. Within the cold dark matter model, the process of dark matter clumping together is gradual. In the universe's infancy, matter should have been distributed with remarkable smoothness, with minor density variations slowly evolving over immense timescales into the filaments, nodes, and voids of the cosmic web. Webb, however, is discovering galaxies that are not only situated closer to one another, but are also arranged in more linear and sometimes more orderly patterns than theoretical frameworks would permit. In the absence of a well-developed dark matter scaffolding, this degree of organization should not be possible. This raises a fundamental question about the origin of such early order. If dark matter lacked the necessary time to arrange itself into these intricate structures, perhaps its fundamental nature is different from what we have supposed. One possibility is that it is not as cold as the lambda CDM model suggests. If dark matter were warm or self-interacting, it might aggregate more rapidly or distribute itself in a different manner. However, these modified dark matter theories introduce their own set of challenges and do not perfectly reconcile with other cosmological observations like those of the cosmic microwave background or the dynamics within galaxy clusters. A second possibility is that alternative theories of gravity, long considered on the periphery of mainstream thought, may warrant a renewed examination. Models such as MOND, or Modified Newtonian Dynamics, and its relativistic extension, TAVS, try to account for galactic rotation and structure without invoking dark matter at all, instead proposing that the laws of gravity themselves change on vast scales. These theories have historically faced difficulties in explaining the full range of observations, particularly at the cosmological level, but the revelations from Webb could offer new fertile ground for hybrid models that combine modified gravity with a more limited role for dark matter. A third, and perhaps the most profound, implication is that dark matter, as we have conceptualized it for nearly 50 years, might not exist, at least not in the form we have theorized. It is conceivable that our equations for gravity are incomplete, or that our understanding of mass and energy within curved spacetime is flawed. We may be missing an entire layer of physics, one that Webb is beginning to unveil not through direct proof, but through a persistent and growing discrepancy between prediction and observed reality. The significance of this problem cannot be overstated, as dark matter is not merely a placeholder in our cosmological models. Modern astronomy, astrophysics, and particle theory are all constructed upon its foundation. In many respects, it is the central pillar explaining how galaxies form and how the large-scale structure of the universe came to be. Dark matter is the first domino that must fall for the rest of the sequence to make sense. The James Webb Space Telescope cannot directly detect dark matter, as it was not designed for that purpose. But by pushing the boundaries of observable time and resolution, it is testing the predicted effects of dark matter's existence, and those effects are appearing increasingly strained. This has led to a reconsideration of cosmic inflation. For a considerable time, the theory of cosmic inflation has been regarded as one of the most successful explanations for the state of our universe. When first proposed in the early 1980s, it was a radical addition to the Big Bang theory, not as part of the original concept, but as a necessary component to address some of its most significant shortcomings. The central idea of inflation is that the universe underwent a period of extraordinarily rapid, exponential expansion just fractions of a second after the Big Bang. For a brief but crucial moment, space itself expanded faster than the speed of light, stretching the cosmos until it became exceptionally flat, smooth, and uniform. Inflation was conceived to solve deep cosmological puzzles. The horizon problem, for instance, asks why the universe appears homogeneous in all directions, even though widely separated regions should never have had the time to exchange light or information to reach thermal equilibrium. Inflation's answer is that these regions were once in causal contact before the inflationary epoch drove them far apart. Then there is the flatness problem, which addresses why the universe's geometry appears to be perfectly flat, a condition that would be incredibly improbable without some special mechanism. Inflation explains this by suggesting that any initial curvature in a tiny patch of space would be stretched out to near perfect flatness during such a massive expansion. The theory was neat, clean, and mathematically elegant. There was, however, one aspect that inflation did not initially provide: direct, testable predictions. It began as a speculative idea and, for years, remained on uncertain footing. Later theoretical refinements imbued it with greater mathematical rigor, and its predictions, particularly concerning the spectrum of fluctuations in the cosmic microwave background, aligned with remarkable precision to subsequent observations. This success cemented inflation's position within mainstream cosmology, transforming it into standard doctrine. Nevertheless, inflation has always carried a certain aura of contrivance, a solution that felt somewhat like an elegant patch applied to a pre-existing framework. Now, with the aid of early data from the James Webb Space Telescope, the very questions that inflation was designed to resolve are resurfacing. Webb is not observing the inflationary event directly. That moment is thought to have occurred around 10 to the power of negative 36 seconds after the Big Bang, a time so early that even light had not yet come into being. Instead, Webb is examining the structure of the nascent universe, which is a direct consequence of that inflationary period. What we are noticing, as we see more of this early epoch, is that the cosmic architecture appears surprisingly mature, too well assembled, and in some cases, too old. The galaxies Webb is detecting are not just forming sooner than anticipated. They seem to emerge almost fully formed, with substantial masses and orderly rotations, as if they bypassed a chaotic evolutionary process entirely. This is problematic because inflation was specifically engineered to explain the origin of structure by introducing tiny quantum fluctuations into an otherwise smooth, early universe. These minuscule fluctuations were then meant to act as the seeds for the gravitational growth of galaxies, stars, and clusters over hundreds of millions of years. But what does it mean if that structure appears almost instantaneously, without sufficient time for these fluctuations to evolve? The paradox is effectively inverted. Inflation was intended to introduce just the right amount of irregularity into a very uniform cosmos. Yet Webb's early galaxies seem to bypass this phase of chaotic development altogether. They suggest a universe that transitioned directly from inflation, or a similar event, into a state of high complexity. This implies that either inflation operated in a manner very different from our current understanding, or perhaps it did not occur at all. The theory of inflation predicts a very specific spectrum of fluctuations, where certain scales of structure should be more prevalent than others. Even in its earlier stages, the cosmic web displays a curious degree of uniformity, a quality that does not seem to fit comfortably with what inflation should produce. Should this pattern continue to be observed, it might point to a more fundamental conflict between the theory of inflation and the actual observed development of the cosmos. Beyond this, there are also concerns of a more philosophical nature. While inflation offers significant mathematical utility, it also carries some unsettling implications. Frequently, it leads to the concept of a multiverse, suggesting that inflation was not a singular event, but is an eternal process constantly occurring in different regions and spawning an endless number of pocket universes. These other worlds are, by their very nature, unobservable. This makes the theory exceptionally difficult to falsify, pushing it into a domain that feels closer to philosophy than to empirical science. a troubling position for any physical theory. The discoveries from Webb guide us back to a fundamental inquiry. Was a fleeting moment of unimaginable expansion truly necessary to account for the universe as we see it today? Or could it be that we have been using inflation as a way to patch over inconsistencies in a cosmological model that was never as robust as we had assumed? A number of scientists are now revisiting older concepts, such as bouncing or cyclic cosmologies, which propose that the universe began not with a singularity, but from the collapse of a preceding cosmos. Still, others are investigating quantum gravity frameworks, where space and time themselves are emergent properties, potentially eliminating the need for an inflationary period altogether. This leads to the problem of the overly smooth universe. A common conception of the early cosmos is that of a chaotic soup of high-energy particles and intense turbulence. From this fiery origin, the universe was expected to evolve slowly, with dense patches gradually forming that would later become the foundations for galaxies and larger structures. When cosmic inflation was incorporated into the Big Bang model, the prediction was that the primordial universe would be predominantly smooth, yet marked by minor imperfections. These were thought to be quantum ripples, stretched to cosmic scales, creating subtle variations in density. These tiny irregularities were considered essential. They were the necessary flaws that would permit structure to emerge. A universe that was perfectly uniform, after all, would have stayed that way forever. Galaxies require gravitational anomalies, lumps, and gatherings of matter to attract the gas and stars needed for their formation. Without such imperfections, there is nothing to coalesce into stars, planets, or beings like us. These very flaws are, in fact, detectable within the cosmic microwave background, or CMB, where they appear as slight temperature differences, the lingering imprints of those initial seeds. While the CMB does reveal these tiny fluctuations as anticipated, the images from the James Webb Telescope of the early cosmos do not seem to reflect the chaotic aftermath that these seeds should have sown. Webb appears to be observing a universe that is too orderly, too symmetrical, and too placid to be one still in the throes of assembling its primary structures. This is not the kind of tranquility that arises from simple uniformity. The issue is not that galaxies are distributed in an even pattern. Instead, they are materializing in locations, quantities, and forms that are difficult to account for. The larger point is that the pace and organization of how structure is forming seems far too refined and mature for how early it is occurring after the Big Bang. Galaxies are appearing with well-ordered spins, clusters are assembling with remarkable consistency. The expected messiness is conspicuously absent, which is a disquieting observation. The inflationary model predicts that the initial fluctuations should have led to clumpy, uneven distributions in the universe's early phases, regions of greater and lesser density that would slowly collapse into ever more intricate arrangements. Webb, in contrast, is finding galaxies that seem to have sidestepped that chaotic period entirely. In certain fields of observation, there is a startling consistency in their size and shape. Structures that should have taken billions of years to develop appear to be fully formed only a few 100 million years after the Big Bang. This particular challenge echoes a criticism some scientists have leveled against inflation itself, that it solved the universe's initial problems a little too well. It is conceivable that inflation made the cosmos excessively smooth by expanding space with such speed and efficiency that it left insufficient texture for structure to develop in the manner we observe. If this were true, the galaxies Webb is seeing should not be able to exist, and yet they are clearly there. Some researchers have suggested that our models of early gravitational collapse could be incomplete. It is possible that gas and dark matter came together more rapidly than we currently believe, but even this idea has its limitations. Gravitational systems simply require time to develop. Increasing the efficiency of star formation or postulating the existence of unusually cold dark matter does not readily explain the sheer scale of the structures being witnessed. Others suggest that the cosmological simulations we use to forecast the formation of structure might be too simplistic. It could be that the universe does not evolve according to the rules we have programmed into our models. If this is the case, however, it casts doubt on the validity of decades of predictions that were built upon those very simulations, including our understanding of the early universe's fundamental shape. There is also the chance that this smoothness is merely an observational artifact, that we are witnessing galaxies that formed exceptionally early because of some unknown physical process, while the rest of the cosmos developed more slowly. But as Webb continues to survey the early universe, this explanation becomes increasingly difficult to defend. The so-called anomalies are simply becoming too widespread to be dismissed as isolated occurrences. A related cosmic mystery, connected to the too smooth problem, is the question of why the universe's structure is so exquisitely balanced on the larger scales. How is it that the expansion rate, the distribution of matter, and the overall curvature are all so perfectly aligned to allow for the formation of galaxies in the first place? Scientists had believed that inflation provided the answer, but Webb's findings imply that the precision might be even greater than what inflation would predict. It is almost as if the cosmos was following a deliberate blueprint from the very beginning. What if the primordial universe was not a chaotic state from which order gradually emerged, but was instead something more like a pre-configured system? This would be a cosmos that did not have to build complexity over time, but one that began with that complexity already encoded within it. Such a scenario would demand a complete rethinking not only of how structure forms, but of the universe's initial conditions, or perhaps even the absence of a singular beginning at all. This brings us to James Webb and the problem of the impossible early galaxies. It was perhaps inevitable that at some point these objects would be described as impossible. This is not meant in a poetic or metaphorical sense. The term is used because, according to our standard understanding of physics, they simply cannot exist. The very first deep field images from the James Webb Space Telescope revealed galaxies that do not conform to expectations. They are too massive, too luminous, too mature, and most disturbingly, far too numerous for any plausible location on the Big Bang's timeline. Astronomers had anticipated that Webb would discover primitive formations, small, disordered, gas-heavy clouds that were still in the process of coalescing into the first galaxies. Astronomers had anticipated witnessing the chaotic dawn of cosmic structure, a period where the first stars were just beginning to flicker into existence, and galaxies were assembling gradually over vast stretches of time. What the James Webb Space Telescope revealed, however, was something entirely different and far more developed. The telescope uncovered galaxies that were already fully formed, their light shining from redshifts of 10, 12, and even greater values. These were structures that existed when the cosmos was merely a few 100 million years old. The startling nature of these galaxies was not just their presence at such an early epoch. The true puzzle was how much they had seemingly achieved in such a short window of time, making their existence appear impossible under current theories. Some of these ancient galaxies contain a stellar population comparable to our own Milky Way. Others display remarkably mature features, such as well-defined disks, stable rotational patterns, and a chemical composition suggesting they had already cycled through multiple generations of stars. They did not resemble infant galaxies. They looked like fully grown structures inhabiting a universe that was still in its infancy. One of the most compelling examples is a galaxy designated Sears 93,316, which has a measured redshift of approximately 16.7. This value means we are observing it, as it was just 240 million years after the Big Bang. According to established cosmological models, a galaxy like this should not have had nearly enough time to form even its first population of stars, let alone reach such a state of maturity. And yet, the images show it clearly, an organized and luminous object. The reason these galaxies are deemed impossible is not merely their early appearance. The issue is that the timeline for how stars form, mass accumulates, and complex structures are built is rooted in well-established physical principles. The processes involved are inherently time-consuming. Gas clouds require significant time to cool down and collapse under gravity. The birth of stars depends on reaching specific density thresholds and triggering gravitational instabilities. Furthermore, the enrichment of a galaxy with heavier elements, or metals, necessitates the life and death of several successive stellar generations. None of these are events that can be accelerated arbitrarily. Nevertheless, these early galaxies seem to have accomplished all of this within the first 2% of the universe's total lifespan. When Webb first started sending back its initial data, a common assumption was that some of these objects were being misinterpreted. Scientists theorized that their redshifts might be overestimated due to issues like photometric confusion or contamination from light emitted by closer objects. However, as spectroscopic confirmations began to arrive, the reality of the situation became undeniable. The high redshifts were accurate, and therefore, so were the incredible ages of these galaxies. This has prompted a growing consensus within the astrophysics community that some part of our standard cosmological model must be incorrect. Some theorists have put forward the idea of revising star formation rates, proposing that these primordial galaxies were exceptionally more efficient at converting gas into stars than their modern counterparts. Others have suggested the existence of a new type of ultra-dark matter halo that could have sped up the process of gravitational collapse. But these adjustments are like patches on a larger problem, and they introduce new complications of their own. If star formation was once so incredibly efficient, for instance, why is similar behavior not observed in more recent cosmic epochs? If mass could collapse with such rapidity, what does that imply about the fundamental nature of dark matter or the potential influence of unknown cosmic forces? Perhaps the most fundamental question that keeps arising is why our models failed to predict this outcome. For decades, our expectations about the appearance of the early universe have been shaped by cosmological simulations. We developed a comprehensive framework known as the LCDM model, which provided a narrative for when galaxies should emerge, what their sizes should be, and how they ought to develop over time. But the Webb telescope has essentially pulled back the curtain on this cosmic stage, revealing it to be filled with mature actors long before the play was scheduled to start. The unease among researchers isn't just about the presence of these advanced worlds. It's about the implication that our entire conception of the universe's timeline and assembly might be fundamentally flawed. If the cosmos did not experience a slow, incremental buildup of complexity but instead made a rapid leap into it, what other assumptions about the early universe might also be wrong? The problem of these impossibly early galaxies now stands as one of the most significant and intensely debated mysteries in all of astronomy. The issue is more than just a single anomaly. It represents a potential threat to the entire cosmic timeline, demanding either a radical revision of our existing ideas or the formulation of a completely new model. Contemporary astronomy is founded on the principle that complexity increases with time. Galaxies are not expected to simply switch on like light bulbs. They are understood to evolve. They are thought to begin as vast clouds of hydrogen and helium, which coalesce due to gravity, ignite their first stars, accumulate heavier elements from stellar death, and gradually transform into the dynamic structures we observe in the universe today. This entire process of cosmic maturation, from simplicity to complexity, was believed to require billions of years. The James Webb Space Telescope, however, is presenting a different story. It is a narrative in which the early universe did not necessarily undergo a slow, gradual evolution, but may have emerged already highly structured. In each of its deep field observations, Webb continues to find galaxies that appear remarkably complete. They do not look like they are in the process of becoming something or still assembling their parts. They are simply there, boasting star formation rates that can match modern galaxies, exhibiting disks, bulges, and even spiral arms, and showing chemical signatures that point to extensive stellar recycling. These are not preliminary sketches. They are like polished final chapters appearing only a few 100 million years after the Big Bang. Our models predict that the cosmic dark ages, the era between the release of the cosmic microwave background radiation and the ignition of the first stars, should have lasted for about 200 to 300 million years. Throughout this period, the universe was cooling, and gravity was only just beginning its slow work of pulling together the first neutral atoms. Following this phase, the very first stars and galaxies were expected to start forming as small, messy, and metal-poor systems. But what Webb is revealing is a universe that seems to have bypassed this awkward adolescent stage entirely. Some of the galaxies it has found possess stellar masses on par with the Milky Way. To achieve this, they would have needed to form stars at an astonishing rate, converting gas into suns with an efficiency that no current model can adequately explain. Even the most extreme starburst scenarios, which are known to trigger rapid bursts of star formation, fail to account for how such massive galaxies could exist so early in cosmic history. If galaxies could form so quickly and so completely, it suggests our timeline for cosmic evolution is incorrect, perhaps by orders of magnitude. This raises the unsettling possibility that the universe was not a slowly unfolding story, but was somehow preloaded with structure, waiting to be seen. What would it mean if the universe did not evolve in the way we thought, but instead began in a state that was already evolved? The great appeal of the Big Bang model has always been its explanatory power, its ability to narrate the journey from ultimate simplicity to profound complexity. But if complexity was present from the very beginning, that entire story must change. The narrative shifts from one of gradual emergence to one that feels more like an abrupt appearance. This does not necessarily imply magic or intelligent design, but these are the profound questions that arise when scientific observation pushes beyond the boundaries of established theory. One possibility is simply that our understanding of how the universe began is fundamentally incomplete. It is conceivable that the physical laws governing the formation of cosmic structures in that primordial era were entirely different from the ones we observe today. Perhaps the principles that shaped the cosmos then are no longer in effect, or, in a more profound departure from our assumptions, maybe time itself did not function in the way we currently comprehend it at the very start of everything. There is also the chance that our cosmic yardstick is flawed. If the redshift of distant objects is not a reliable measure of their age, and if our calculations of distance and time are consequently inaccurate, then these galaxies may not be as ancient as they appear. This adjustment would grant us some breathing room, but only a very small amount. Even the most generous recalculations cannot transform a few 100 million years into the vast billions of years required for our models of galaxy evolution to hold true. Adding to the complexity is the remarkable uniformity of these early galaxies. If the early cosmos contained isolated pockets of accelerated development, that would be puzzling enough. But what the Webb telescope is revealing seems to be a consistent, widespread pattern. We are not seeing one or two rogue galaxies that broke the cosmic rules, but entire populations of them. This level of consistency strongly suggests that this was not a rare fluke. It was, in fact, the standard for that era. Some cosmologists have begun to describe the early universe with an evocative metaphor, a stage that is already perfectly set. When the lights come on, the actors are already in costume, ready to deliver their lines without any rehearsal. There is no period of preparation or gradual development. The image is of a universe that was born ready, organized, and fully functional. Such a picture is difficult to align with a cosmological model built upon the principle of gradualism. It implies that whatever processes were at work in the nascent universe, they were dramatically faster, more efficient, and more organized than anything accounted for in the standard model. This raises a pivotal question. Were we observing the cosmic dawn, or was it actually cosmic noon? For decades, scientists have anticipated the day they could finally peer into the cosmic dawn. This term describes the moment the first stars ignited, ending the cosmic dark ages and filling the universe with light. That epoch was expected to be a quiet, tentative time. The first stars would have been scattered across the cosmos, their light just beginning to flicker within a vast sea of neutral hydrogen as the first galaxies started to coalesce. Our view of this period was supposed to be a glimpse into the slow, gradual emergence of structure from nothingness. Yet, with the first streams of data from the James Webb Telescope, a rather haunting possibility has come into focus. What if the universe's supposed dawn was already the middle of the day? What if the event we imagined as the gentle sunrise of creation was, in reality, the bright, bustling midday of a cosmic cycle, far more developed than any origin story had predicted? The phrase cosmic dawn inherently suggests a beginning the first light, the hesitant start of an evolutionary process. But the galaxy's Webb is observing at redshifts of 10, 12, and even as high as 16 are not hesitant or dim. They are luminous, structured, and dynamic. They are forming stars at rates that rival those of many modern galaxies. Some even appear to outshine galaxies that exist billions of years later in cosmic history. This is not a mere flicker in the void. It is a brilliant blaze. This paradigm shift is more than just a beautiful discovery. It challenges the very narrative of cosmic history. Our expectation was that the universe would start slowly, building in complexity generation by generation over immense timescales. Webb, however, presents us with a universe that seems to have skipped its formative years and jumped directly to a mature state. It is not just that these early galaxies are bright, they are too bright, their development too rapid, and their presence too synchronized. They appear across the sky not as isolated oddities, but as a coherent population. Many display advanced features like established disks, significant metal content, and organized rotational motion characteristics that should require more time, recycling of materials, and gravitational growth than the Big Bang timeline seems to permit. The implications of this are enormous. If this is truly a cosmic noon, it compels us to reconsider whether the period we have been calling the early universe is early at all, at least not in the sense we have understood it. It opens the door to the possibility that the universe was already well into a previous stage of evolution before the Big Bang. It is also plausible that the birth of light we are witnessing was not a beginning, but a renewal, a reset, or a re-illumination of a pre-existing cosmos. Some theoretical frameworks, such as cyclic or bouncing universe models, propose that our universe is just one phase in an eternal sequence of expansions and contractions. In these models, the Big Bang is not an absolute origin point but a moment of transition, much like the chime of a clock that marks a new hour but not the beginning of time itself. The data from Webb might be lending new observational weight to these speculative ideas. After all, if mature galaxies are already flourishing at redshifts greater than 12, then what came before them? What provided the initial seeds of their structure? What conditions could have possibly allowed for such incredibly rapid star formation and complex organization? The principle of entropy also comes into play. According to standard thermodynamics, entropy, or disorder, should increase over time. A universe that began in a hot, dense, and uniform state should gradually become less ordered. But Webb is showing us a high degree of early organization, a cosmos that is remarkably well assembled rather than chaotic. This unexpected order points to either an initial low-entropy state that we have not yet conceived of, or perhaps a memory of a previous, more structured cycle carrying over into our own. Some scientists are now even contemplating whether we are observing not just early light, but inherited light. This would mean that the structure and organization we see today originated in an era before the Big Bang. In this view, the cosmic dawn was not the universe taking its first breath. Instead, it was the moment the curtain rose again following an intermission. Of course, this remains in the realm of speculation for now. The research from Webb is still new, and interpretations of its findings are constantly evolving, but the overarching trend is difficult to dismiss. There are simply too many bright galaxies and too many diverse types for a slow, patient dawn to be a fitting description. The scene looks more like the start of a day for a universe that is already wide awake and deep into its existence. This forces a re-evaluation not just of when the universe began, but of how beginnings themselves work. If what we thought was the beginning turns out to be the middle, then either our understanding of time is flawed, or we have been reading from the wrong chapter of the cosmic story. This brings to mind an alternative model for the universe's origins that once rivaled the Big Bang, the steady-state theory. Developed in the late 1940s by Herman Bondi, Thomas Gold, and Fred Hoyle, this theory painted a radically different picture of reality. It described a cosmos that had no beginning and no end. In their model, the universe was indeed expanding. However, as it expanded, new matter was continuously and spontaneously created throughout space, ensuring that the overall density remained constant. There was no singular, explosive moment of creation, no single point of origin. There was only an eternal universe that, on the grandest scales, appeared fundamentally the same at all locations and at all times. For several decades, the steady-state theory stood as a serious scientific competitor to the Big Bang model. The steady-state model held a certain philosophical charm, appealing to the desire for a universe that was eternal, fundamentally unchanging on the grandest of scales, and unburdened by the complicated notion of a singular beginning. But in the 1960s, this perspective met a serious challenge with the discovery of the cosmic microwave background radiation, or CMB. This faint, uniform glow of residual heat permeating space was a direct prediction of the Big Bang theory, yet it was something the steady-state model could not readily explain. From that moment, the Big Bang theory ascended to its dominant position, and the steady-state concept was largely set aside, viewed as a relic of outdated cosmology. That is, until now. The reason for this quiet reconsideration lies in the data coming from the James Webb Space Telescope. It isn't that Webb is definitively disproving the Big Bang, but its observations are revealing apparent cracks in the standard model. We are seeing galaxies that seem to have formed too early in cosmic history, stars with a chemical composition that should have been impossible at that epoch, and supermassive black holes that seemingly shouldn't exist for billions of years. The picture emerging is of a universe that looks surprisingly mature and organized far earlier than our standard timeline would permit. These findings are eerily more consistent with a cosmos that has been evolving for a very, very long time, rather than one that emerged from a single point just 13.8 billion years ago. While the steady-state theory does not account for everything Webb observes, it does offer a framework for thinking about this timeless sense of organization. Within this model, there is no need to rush the formation of galaxies. There is no puzzle of how black holes grew so massive so quickly. If the universe has always existed, then complexity does not need to erupt from nothingness. It can unfold slowly and perpetually across a timeline with no beginning and no end. The steady-state concept, however, still faces significant hurdles. The cosmic microwave background is still present, and it remains difficult to reconcile with the idea of continuous matter creation. This has led some cosmologists to wonder if the best elements of both models could be combined. What if the early universe was not an absolute beginning, but instead emerged from a preceding cycle? What if the era we call early is actually a late chapter in a much larger story? Modern variations of the steady-state idea build upon this thinking. Quasi-steady-state cosmology, or QSSC, which was proposed by Hoyle and others later in their careers, introduced the concept of periodic mini-bangs, localized creation events scattered throughout an eternal cosmic framework. Now, in the age of Webb, this idea no longer seems quite so far-fetched. The galaxies we are observing at high redshift do not look like the very first galaxies. They appear more like the latest generation in a long lineage, galaxies that could have formed in cosmic conditions already enriched by the passage of immense time. Webb has also complicated our assumptions about the expansion of the cosmos. If this expansion does not follow the clean, exponential trajectory once believed, if it is instead influenced by unknown physics, phantom energy, or quantum effects, then the entire clockwork of Big Bang timing could be miscalibrated. A universe that expands more slowly, or one that expands in cycles, would grant more time for early structures to form, again favoring the long-term perspective inherent in steady-state ideas. It is important to note that very few cosmologists are advocating for a return to the original steady-state theory. They are, however, beginning to dust off its core concepts and re-examine them in light of new information. This is a natural part of the scientific process. When the prevailing model begins to show signs of stress, requiring ever more elaborate explanations while its predictive power diminishes, it is only logical to revisit the alternatives. Another idea, plasma cosmology, has long existed as a controversial but persistent alternative in the background of standard cosmology. It questions not only when the universe began, but the very mechanism of its formation. This concept does not start with a bang, but with the fundamental power of plasma. Plasma cosmology proposes that the universe is shaped not primarily by gravity, but by plasma, the fourth state of matter, and the electromagnetic forces that dictate its behavior. Developed in part by the Nobel Prize-winning physicist Hannes Alfvén, this model suggests that the cosmos is an eternal interplay of charged particles, vast electric currents, and cosmic-scale magnetic fields. Where the Big Bang describes a hot, dense, explosive birth, plasma cosmology sees no beginning at all, only the continuous exchange of energy within an infinite universe driven by electrical forces. In a cosmos dominated by plasma, matter would not condense solely under the gentle influence of gravity. Instead, charged particles would respond to electromagnetic fields, which are an astonishing 10 trillion times stronger than gravity. These fields could channel, shape, and organize matter into the filaments, voids, and spirals that we actually observe when mapping the large-scale structure of the universe. That cosmic web of galaxies and clusters, rather than being a relic of gravitational clumping in a primordial soup, might instead be the product of immense electric currents forming plasma filaments across space. For For decades, plasma cosmology was largely dismissed. It struggled to explain the cosmic microwave background and could not predict the relationship between redshift and distance as effectively as the Big Bang model. But the new results from the James Webb Telescope are compelling some cosmologists to take another look. This is because the Galaxies' web is seeing too young, too organized, and too massive strain the timeline allowed by a gravity-driven universe. They might, however, make more sense in a cosmos where plasma is the dominant force. Stars and galaxies could form much more efficiently in such an electrically active universe. Instead of gas clouds slowly collapsing under their own gravity, powerful plasma currents could rapidly draw matter together into strands, while magnetic fields would constrict them in a process known as the Bennett pinch. These electromagnetic interactions could trigger powerful bursts of star formation, quickly building galactic structures and enriching the cosmos with heavier elements. A pattern seems to be emerging. It is not a coincidence that plasma cosmology anticipated some of the very phenomena Webb is now discovering. This is not because the theory is magical, but because its mechanisms inherently allow for speed and structure without the long timelines demanded by gravitational collapse. And since plasma makes up over 99% of the visible matter in the universe, from stars and nebulae to the space between galaxies, the theory insists that we have been ignoring the true engine of cosmic architecture. The early galaxies revealed by Webb are not just primitive, they are electrifyingly complex. Some are already arranged in filamentary structures, aligned in what appear to be embryonic versions of the cosmic web. That kind of order, that degree of large-scale connectivity, simply should not exist so soon after a supposed beginning, if gravity alone was responsible for all the heavy lifting. Within plasma cosmology, however, this structure is precisely what is expected from a network of charged matter shaped by electric currents on both galactic and intergalactic scales. The question of redshift is also addressed from a different perspective. Instead of resulting solely from the stretching of space through cosmic expansion, this model proposes that redshift could be an effect of photons interacting with intergalactic plasma. This interaction would cause them to lose energy as they travel immense distances through an electrically active medium. Such a process would fundamentally alter how we measure cosmic time and distance, implying that the most ancient galaxies might not be as far away or as old as we currently believe. It is important to be clear that plasma cosmology remains a deeply contentious topic. The level of consensus for this model does not compare to that for the Big Bang. It lacks a comprehensive theory for the cosmic microwave background, and it has struggled to produce predictions that align with modern observations. Even so, there are now cosmologists bold enough to ask whether it was a mistake to dismiss the role of plasma. As the Webb telescope challenges one model after another, this question gains new relevance. There is also a cultural context to consider. Plasma cosmology was never afforded the same attention as its rival. It saw a brief period of interest in the mid-20th century but quickly fell out of favor. Not necessarily because it was disproven, but because the Big Bang theory had gathered significant momentum, institutional support, and the perceived mathematical elegance of inflation and general relativity. Plasma cosmology did not offer such clean mathematics. Its foundation was in the complex dynamics of real-world physics, chaotic, non-linear, and notoriously difficult to model. But perhaps the universe itself shares these messy characteristics. The James Webb Telescope is peeling back a layer of the cosmos we have never been able to see before. What it is revealing may not be the simple aftermath of a singular bang, but rather the intricate patterns of a living, electric cosmos, structured by forces more immediate than any ancient explosion. This leads to another profound debate: the Big Bang versus the Big Bounce, a universe that may have had no beginning at all. For almost 100 years, the Big Bang has been the standard story of how everything came to be. It describes a single, infinitesimally small point from which all space, time, and matter erupted into existence. According to this model, time began approximately 13.8 billion years ago, and the universe has been expanding ever since. But what if that story is incomplete? What if the universe has been in motion for all of eternity and never truly started? This is the world of the Big Bounce, a radical alternative that suggests our universe is merely the latest iteration in a cosmic cycle of expansions and contractions, an eternal heartbeat echoing across time. This view replaces a singular explosion with the idea of a continuous rhythm, where the universe collapses upon itself before rebounding into a new phase of expansion. And now, as the James Webb Telescope gazes deeper into the cosmic past, some scientists are beginning to wonder if the evidence aligns better with a loop than with a straight line. At the heart of this divergence is the concept of the singularity, a point of infinite density and temperature where the known laws of physics cease to apply. This mathematical oddity, a moment when all our equations fail, is a key component of the Big Bang model. The Big Bounce, however, elegantly sidesteps the singularity altogether. From this viewpoint, the universe never truly ends or begins. Instead, it contracts to an incredibly small size and then expands outward again, driven by quantum effects, pressure from exotic forms of matter, or unknown physics related to gravity at the smallest scales. The reason this idea is being revisited now is that James Webb's discoveries are unsettling the linear timeline. The presence of massive, well-structured galaxies far too soon after the supposed beginning of time hints at a pre-existing order, perhaps even the lingering memory of a prior universe. In a universe that cycles back and forth, each phase could leave behind patterns and information that influence the next. This might explain why the earliest galaxies appear so developed. They are not strange anomalies. They are inheritances, complexities passed down from a previous cosmos that collapsed, reset, and planted the seeds for the one we inhabit today. This is more than just a philosophical exercise. The Big Bounce has a basis in theoretical physics. In models of quantum gravity, particularly those arising from loop quantum cosmology, or LQC, a quantum bounce takes the place of the Big Bang singularity. According to these models, when space-time becomes intensely dense, quantum effects generate a repulsive force that halts the collapse and initiates a new era of expansion. Time is transformed, not terminated. There is even some observational motivation for this. The smoothness and structure of the cosmic microwave background, along with the early appearance of galaxies seen by Webb, can be interpreted as signs of a pre-existing order, if the universe is older than we think, not 13. 8 billion years old, but eternally old, then there is no need to explain how complexity arose so quickly. It didn't. It was here before. In a one-shot universe, entropy increases until everything fades into a cold, uniform death. But in a bouncing cosmos, entropy might be reset or recycled with each bounce. It is also possible that the bounce occurs in a way that preserves structure across cycles, allowing galaxies and even black holes to leave imprints on the next iteration. Of course, there are significant problems to solve. A primary challenge is thermodynamics. How does a cyclical universe prevent the endless accumulation of chaos? Each cycle would presumably be more disordered than the last. Some models propose that each bounce makes the universe slightly larger, which would dilute the chaos. Others invoke speculative processes for offloading entropy into other dimensions or branes, ideas rooted in string theory. Another question is whether we can prove it. Finding traces of a previous universe would require us to look for specific markers in our own, such as imprints in the microwave background, unusual anisotropies, or persistent gravitational waves. Some cosmologists suspect these clues may already be present in the data, hiding in plain sight but mistaken for noise or other artifacts. This re-examination of cosmic origins is also reviving interest in the tired light hypothesis. For a very long time, redshift has been used to measure the distance between galaxies. The more a galaxy's light is stretched toward the red end of the spectrum, the farther away it is, and the longer ago it must have emitted that light. Modern astronomy is built upon this idea so firmly that it is taken as a given. Redshift is understood to mean expansion, which in turn is seen as proof of the Big Bang. But what if it does not? An alternative explanation, an old one that was long dismissed, is now seeing a quiet resurgence in light of the James Webb Telescope's revelations. An alternative perspective, known as the tired light hypothesis, puts forth a profoundly different interpretation of cosmic redshift. This idea suggests that light does not redden because the universe is expanding, but rather because it progressively loses energy as it traverses the vast distances of space. In this framework, photons, the fundamental particles of light, are thought to gradually fatigue through interactions with the cosmic medium. This reduction in energy causes their wavelength to shift toward the red end of the spectrum, mimicking the effect of a receding object. However, there is no actual recession involved, no expansion of the universe, and no stretching of space-time itself. Instead, light is simply thought to deplete its energy, much like a battery winding down on its long passage through an ancient and potentially infinite cosmos. This concept was first proposed by Fritz Zwicky in the 1920s, offering a stark contrast to the emerging idea of an expanding universe. As the Big Bang theory gained prominence, the tired light hypothesis faded into relative obscurity. It encountered criticism for its inability to account for certain observations, such as the way the light curves from distant supernovas appear to stretch over time. It also lacked a specific physical mechanism to explain how light could lose energy without scattering or causing distant objects to appear blurry. Nevertheless, the idea never completely disappeared. Now, with the James Webb Space Telescope revealing galaxies that appear far too developed for their supposed age based on redshift, the tired light model is quietly re-entering scientific discussion. If these galaxies are not as distant or as ancient as their redshift would imply under the standard model, then the entire cosmic timeline would need to be radically compressed, and in the process, many of the Big Bang's most persistent puzzles could simply vanish. According to a tired light theory, the large, early galaxies observed by Webb might not be early at all. While their redshift remains high, it would not serve as a timestamp of their age. Instead, it would act as a measure of distance, indicating the cumulative energy their photons have lost on their journey to us. This would imply a universe that is not expanding away from itself but is instead static, or perhaps even boundless and eternal. Galaxies would not be flying outward from a singular origin point. They would simply exist, distributed throughout space-time, with their light aging as it travels toward our telescopes. From this viewpoint, some of the challenges posed by Webb's data find an elegant resolution. The galaxies would have had ample time to develop, meaning they are not growing too rapidly. The supermassive black holes at their centers are not forming impossibly early. They are simply very old, their growth having occurred over a long and gradual period. The metal content of their stars no longer conflicts with models of galactic evolution, but instead points to a universe that has existed for a very long time. The tired light hypothesis, however, continues to face scrutiny. A significant objection is the absence of image blurring. If photons were losing energy through interactions, one might expect those same interactions to scatter the light, making distant galaxies appear fuzzy. Yet, newer versions of the theory propose more subtle mechanisms that could avoid this effect, such as quantum-level energy leaks or interactions with some unknown property of the vacuum of space. Another major hurdle is explaining the cosmic microwave background. In the Big Bang model, this faint radio noise is understood as the residual radiation from an initial hot, dense state. The tired light hypothesis does not yet offer a direct replacement for this explanation. Some proponents suggest the CMB could be re-examined through a different lens, perhaps as steady background radiation in an eternal universe, or as the combined, diffused emissions from innumerable distant galaxies over cosmic time. While these remain speculative ideas, they are no longer dismissed as entirely implausible. What gives the tired light concept new relevance is the remarkable precision of the Webb telescope. We are now observing distant galaxies with a level of detail that was previously unimaginable, and their apparent maturity is difficult to reconcile with the standard, expansion-driven timeline. If the very foundation of that timeline, the assumption that redshift equates to distance and age, is flawed, then our entire cosmological chronology is thrown into question. The re-emergence of this idea is not driven by nostalgia or a desire to be contrarian. It stems from a fundamental scientific question. Have we mistaken a measurement for its meaning? Redshift is undeniably telling us something important about the cosmos, but what that something is remains an open subject of inquiry. The James Webb Telescope is not on a mission to prove or disprove tired light. However, its observations of galaxies that seem too evolved, structures that appear too organized, and timelines that feel too compressed are breathing new life into old doubts. These are doubts which suggest that our interpretation of light's journey across space may be a more human-centric perspective than a universal truth. The cosmic microwave background, or CMB, has long been celebrated as the most compelling evidence for the Big Bang theory. It represents the oldest light that we can detect, originating from an era approximately 380,000 years after the universe's proposed beginning. This was the moment when the cosmos had cooled sufficiently for atoms to form, allowing photons to travel freely through space for the first time. The CMB's faint, uniform glow was first detected in 1965 and is often poetically described as the afterglow of creation, a snapshot of the infant universe, frozen in time. But an intriguing question is now being asked. What if our reading of that snapshot has been incorrect? The James Webb Space Telescope was not designed to observe the CMB directly, as it is tuned to infrared rather than microwave wavelengths. Its purpose is to see what came next. By peering deep into the epoch when the first stars and galaxies ignited, Webb is effectively building an observational bridge between the CMB era and the modern universe. And it is on this bridge that cracks are beginning to appear. The issue is that the CMB provides a very specific blueprint for how the universe should have evolved. Satellites such as COBE, WMAP, and Planck have meticulously mapped incredibly small variations in its temperature. These subtle fluctuations are believed to be the quantum seeds from which all cosmic structure eventually grew. The patterns within the CMB informed our understanding of how much matter the universe contained, how clumpy it was in its infancy, and what kinds of structures we should expect to find at various points in cosmic history. Yet, the James Webb Telescope is discovering more structure, more complexity, and more massive objects at earlier times than the models based on the CMB had predicted. This discrepancy is a significant concern. If the CMB truly represents the universe's initial conditions, then how did structure form so efficiently and so quickly? This suggests one of two possibilities. Either our understanding of how matter aggregates from the initial state is incomplete, or the CMB itself does not tell the entire story of the universe's origins. One of the central issues lies in the scale of the fluctuations. The CMB shows temperature variations of only about 1 part in 100,000, indicating an astonishingly smooth early universe. This uniformity has always presented something of a puzzle, as it should take an immense amount of time for such a smooth distribution of matter to evolve into the lumpy cosmos of stars, galaxies, and filaments that we observe today. The theory of cosmic inflation was introduced precisely to address this, proposing a period of rapid expansion that would stretch and smooth the early universe while preserving just enough imbalance for structure to form. But Webb's discoveries of early galaxies appear too lumpy, too soon. It is as if the seeds of structure were either larger or grew far more rapidly than the CMB model allows. This could mean one of two things. This presents a difficult choice. Either the universe's structure formed in a way that was uninfluenced by the initial conditions revealed in the CMB, or the conditions we have long assumed for that early epoch were not accurate. Another challenge arises from uniformity. The cosmic microwave background is characterized by its remarkable isotropy, a quality indicating that it appears the same in every direction we look. However, the Webb telescope has identified patches of the sky that contain an unexpectedly high number of early galaxies. This observation could suggest that the CMB's smooth picture overlooked localized density fluctuations, or it might challenge the fundamental idea that the cosmos is homogeneous on the largest scales. If the primordial universe was not as uniform as the CMB suggests, then some unknown process must have occurred between the time the CMB was emitted and the formation of the first galaxies. Alternatively, perhaps the CMB itself is not the faithful messenger from the past we believe it to be. An even more profound concern emerges, that our fundamental interpretation of the CMB might be entirely incorrect. There are other cosmological frameworks which propose that the microwave background is not a remnant of a hot Big Bang. Instead, they suggest it could be the cumulative result of phenomena occurring over a much more extended period. In certain models, such as quasi-steady state and plasma cosmology, the CMB is not viewed as the afterglow from the dawn of time, but rather as a background radiation that has reached a state of equilibrium. This background would be composed of emissions from countless stars, galaxies, and black holes, all stretched out and redshifted across immense cosmic ages. Even within the standard Big Bang model, significant problems remain. The Hubble tension, which is the discrepancy between the universe's expansion rate as measured by the CMB and its rate as measured using nearby galaxies, has not been resolved. While data from Webb is making the local measurement more precise, it only sharpens the issue with our early universe predictions, which are derived from the physics of the CMB. This points to the possibility that the fabric of space and time is more intricate than our theories account for. Although the James Webb Telescope was not engineered to measure the CMB, it is becoming a unique kind of mirror by observing how the universe actually unfolded from that supposed origin point. It is a mirror that reflects not only the predictions of the CMB but also its potential weaknesses. One of the most startling reflections involves the metallicity of early galaxies and stars that seemingly should not exist. In the standard timeline of cosmic evolution, the first stars were expected to be quite simple. These theoretical bodies, known as population 3 stars, were envisioned as massive, brief in lifespan, and, crucially, free of metals. They were believed to have formed purely from the primordial hydrogen and helium created in the Big Bang. In astronomical terms, metals are defined as any element heavier than helium. Such elements can only be forged through nuclear fusion inside stars and scattered by supernova explosions. In the very beginning, these heavier elements had not yet been created. It follows logically, then, that the first stars could not have contained them. If you imagine a chart of cosmic history, metals serve as markers of passing time. As Webb peers deeper into this early era, it has discovered galaxies with metal contents far higher than our models predicted. Some of these ancient galaxies possess metallicities that are equal to or even greater than that of our own Milky Way. Furthermore, they are not particularly old. They appear at redshifts higher than 10, placing them in a period when the universe was merely a few 100 million years old. According to conventional timelines, there simply should not have been enough time for successive generations of stars to form, perish, and disperse these metals across the cosmos. And yet, there they are. These are chemical fingerprints found in a time period where they do not belong. This is not just a minor surprise, it directly contradicts the standard narrative of how stars and galaxies come into being. Based on our prior understanding, the universe at these early stages lacked the raw materials, the metals, to build such complex systems. The consensus was that the first stars would burn intensely and rapidly, then explode to create the first iron, carbon, oxygen, and other heavy elements. We would not expect to see galaxies rich in metals until this cycle of stellar life, death, and metal seeding had repeated itself multiple times. But Webb has found these metal-rich galaxies to be not only early but also widespread. They are not isolated anomalies but entire populations exhibiting a high degree of chemical complexity. The issue is not merely the existence of these metals. The deeper implication is that stellar evolution was somehow greatly accelerated, or that it unfolded in a way completely different from our theories. If the first stars were sufficiently massive, they might have lived and died even more quickly than anticipated, enriching their environments in just tens of millions of years. However, this scenario demands an extraordinary level of efficiency. It requires supermassive stars to form almost immediately after the Big Bang, detonate in coordinated waves, and instantly trigger new rounds of star formation. While not strictly impossible, the required choreography of such events strains plausibility. There is also another, more radical possibility, that the metals were created before the Big Bang. They could have originated either in a phase preceding our universe or as a remnant from the collapse of a prior cosmos. In this view, the universe we observe is not the first chapter of cosmic evolution, but a continuation of a longer story. Webb's discovery of early metallicity would not be evidence of accelerated creation, but rather of transmission from a past cycle. This concept is particularly compelling when considered alongside alternative cosmologies like cyclic models or the Big Bounce theory. In those scenarios, metals and even large-scale structures could potentially survive a cosmic collapse and be carried over into the next phase of expansion. Suddenly, ancient metal-rich galaxies no longer appear premature. Instead, they seem like veterans of a previous reality. This leads to another unsettling question. Were population 3 stars ever real? Despite decades of searching, not a single definitively metal-free star has ever been observed. Every star we have ever seen, even in the most distant galaxies, contains at least trace amounts of metals. It is possible that population 3 stars never existed at all, or perhaps they were so exceptionally rare and short-lived that they left behind no detectable evidence. Or, in a more troubling scenario, what if our entire understanding of the universe's chemical origins is fundamentally flawed? Webb's unparalleled sensitivity allows it to read the spectral lines of distant galaxies with astonishing clarity. Those lines tell a chemical story, one that increasingly deviates from the predictions of standard Big Bang nucleosynthesis. The deeper we look, the more it seems that metals are an intrinsic feature of the early universe, like ink that appeared in a book before the printing press was even conceived. The cosmos is not supposed to be this metal-rich so early on. So, how do we reconcile this? We can adjust our models, imagining extreme scenarios of rapid star formation or redefining what we consider early. Yet each fix makes a model once celebrated for its elegance progressively more convoluted. We could also entertain a more profound possibility. Perhaps the universe's chemical past is not simple, linear, or young. It may be that objects like these galaxies, along with early black holes and primordial gas clouds that do not fit the Big Bang narrative, are teaching us about something older than the Big Bang itself, something far deeper than the timeline we have come to accept. The earliest chapter of the cosmos was once envisioned as a period of profound quiet and simplicity. After the initial expansion of the Big Bang began to slow, the universe was thought to have settled into an immense, dark ocean of neutral hydrogen and helium. These were the lightest elements, forged in the first few minutes of cosmic nucleosynthesis. For hundreds of millions of years, gravity had yet to gather these primordial materials into the first stars and galaxies. During this era, known as the Cosmic Dark Ages, there was no fusion and no stellar death to chemically alter the landscape. It was expected to be a time of undisturbed stillness. However, recent observations from the James Webb Space Telescope, alongside other high-precision instruments, are revealing ancient gas clouds that do not align with this straightforward narrative. These clouds are being found in the distant past, some situated more than 12 billion light-years from us, and they possess characteristics that question nearly every assumption about the early universe. Their temperatures, chemical makeup, physical structures, and densities all present a series of uncomfortable puzzles. The first issue that stands out is their metal content. A number of these gas clouds, which should be untouched by stellar processes, are showing signs of being enriched with heavier elements like carbon, silicon, and even iron. According to the standard model of the Big Bang, these metals simply should not be present. The only known mechanism for producing such elements is the life cycle and eventual demise of stars. If these clouds are genuinely primordial, their composition should be limited exclusively to hydrogen and helium. Their unexpected metallicity implies they were either seeded by a previously unknown generation of stars, or that they exist outside the timeline we have carefully constructed. A second point of contention is that their density and temperature seem incorrect. Some of these formations are cooler than anticipated, suggesting a degree of thermal stability that should not have been possible so soon after the universe's formation. Others are observed to be hotter and denser, which raises the possibility that an unknown form of energy or pressure is influencing them. This opens a path to more exotic ideas, such as the influence of primordial magnetic fields or the lingering heat from a prior cosmic cycle, both of which exist outside the standard Big Bang framework. Then there is the matter of their structure. In the nascent universe, gas was expected to be distributed in a more or less uniform manner, with only minor fluctuations left over from the inflationary period. Yet, some of the gas clouds being detected by Webb and other observatories show complex filamentary, clumped, or even rotating arrangements, as if they were already well on their way to becoming galaxies. That kind of intricate structure should require significant time to develop through the slow work of gravitational evolution, and yet it appears to have been present from the very beginning. This suggests either that the physics governing gas collapse and star formation are far more efficient and aggressive than our models have allowed, or that these clouds are not as ancient as their redshift measurements indicate. A few scientists have started to question whether redshift-based dating, the principle that a higher redshift corresponds to older light, might be giving a misleading impression when applied to these specific phenomena. It's a compelling thought. Could some of these gas clouds be nearer to us in time than they seem, their light perhaps distorted by effects we do not yet fully grasp? It is also interesting that these clouds are found in unusual locations. Their positions do not always correlate with known galactic structures. Some materialize in apparently empty regions of space, while others seem disconnected from any visible areas of star formation. Their immense distance makes it exceptionally difficult to determine their true nature. We are left to wonder if they are failed galaxies, the halos of protogalaxies, or perhaps remnants from a hidden chapter of cosmic history. One particularly unsettling hypothesis suggests that some of these gas clouds could be relics from a preceding universe. They might be fragments from a cosmic cycle that concluded with a collapse and then began anew. In models that propose a cyclical or bouncing universe, material from a previous cosmos could survive and influence the development of the next one. If this were true, these clouds would be more than just anomalies. They would be tangible evidence, chemical and structural fossils of a universe that had to end for our own to be born. While mainstream astrophysics is not yet prepared to embrace such a radical conclusion, the accumulating body of inconsistencies cannot be dismissed. These gas clouds resist easy classification. They are not pristine, they are not uniform, and they are not passive participants in cosmic evolution. They seem to possess a history that predates the official start of the story. In the standard model, complexity builds upward from a simple foundation. First hydrogen, then stars, then galaxies, and finally intricate systems. These enigmatic clouds, however, appear to invert that progression. They emerge on the cosmic stage already shaped, already enriched, and already influenced by forces unknown. This compels us to ask a profound question: what came before the beginning? This mystery connects to another deep puzzle about alien civilizations and the Fermi paradox. For decades, scientists, philosophers, and stargazers have been haunted by a single, persistent question: where is everybody? This is the essence of the Fermi paradox, the stark contradiction between the high probability of extraterrestrial civilizations and the complete, resounding silence we observe. Our galaxy contains billions of stars, many of which are far older than our Sun. This implies that intelligent life should have had ample opportunity to arise, expand across the cosmos, and leave some detectable trace of its existence. Yet, we have found nothing. Now, with the James Webb Space Telescope peering through the veil of the early universe and finding mature galaxies, advanced structures, and other signs of early complexity, the Fermi paradox acquires a darker, more profound dimension. If the universe was capable of forming organized structures much earlier than we once thought, then the potential for intelligent life may have had a head start of billions of years. The data from Webb indicates that galaxies and stars formed with surprising speed, emerging within the first few 100 million years after the Big Bang. This means that planetary systems could have also formed much earlier than our models predicted, bringing with them the possibility of habitable worlds. It is conceivable that entire civilizations rose and fell before planet Earth had even finished cooling, positioning our world as a relative latecomer in cosmic history. The calculus of the Fermi equation is therefore altered. The question is no longer just about whether other life exists. It becomes about why, given potentially eons of time for civilizations to develop, expand, and even transcend biology, we perceive nothing. The silence, in this context, is not merely an absence of opportunity. Instead, it hints that something much more fundamental, or perhaps even unsettling, is at play. One possibility is that we are not truly alone, but simply isolated. The accelerating expansion of the universe, driven by dark energy, is causing galaxies to recede from one another at ever-increasing speeds. Over immense cosmic distances, this expansion makes communication, travel, and even detection not just difficult, but physically impossible. It is conceivable that civilizations have emerged, and even flourished, only to be contained by the sheer structure of space itself, preventing their expansion. A more disquieting notion suggests that civilizations are inherently short-lived. The same cosmic accelerators that enable galaxies to reach maturity so early on might also establish the conditions for rapid self-immolation. If intelligent life did arise in the early universe, it may have extinguished itself long before it could master interstellar communication. As a society's technological prowess grows, so too does its capacity for engineering its own demise, whether through conflict, unchecked artificial intelligence, or catastrophic environmental failure. There is also the unsettling hypothesis that advanced cultures transcend before they ever make contact. Such beings might abandon physical reality entirely, choosing to migrate their consciousness into non-physical domains, such as intricate digital substrates, quantum matrices, or even self-contained, artificial universes. Within these simulated realities, they would have no reason to interact with the cosmos we observe. To such a civilization, our universe might be nothing more than insignificant static, like a forgotten wilderness bordering a vast digital city. The revelations from the Webb telescope do not invalidate any of these ideas. In fact, they lend them greater weight. By revealing a cosmos that achieved structure and complexity far sooner than we imagined, Webb extends the potential timeline for life, and consequently, it also lengthens the history of an unnerving cosmic silence. Then, a truly profound consideration arises. What if other cultures are communicating, but we remain too unsophisticated to perceive their signals? It's plausible that the signatures of intelligence are not radio broadcasts or colossal structures, but subtle manipulations of quantum entanglement, gravitational lensing, or even the cosmic background radiation itself. Considering we are still struggling to fully comprehend what Webb is showing us about the cosmos, it seems a monumental challenge to recognize the handiwork of minds potentially billions of years our senior. There is, however, a final, more hopeful viewpoint. It is possible we have not yet detected any extraterrestrial signals because we are the first to emerge. Not just the first, but the inaugural species to achieve consciousness in a cosmos that is still young and awakening. The discoveries from Webb may indicate early organization, but they are not definitive proof of life. Perhaps worlds with stable, carbon-rich environments suitable for life are exceedingly rare. Perhaps intelligence itself is not an inevitable outcome, but an extraordinary anomaly, and we, in our strange and fragile existence, might just be the first voice in an otherwise quiet universe. That voice could either fade into the void, or perhaps initiate a conversation that spans eons. But this leads to an even deeper question. Did the universe have a beginning at all? The concept of a cosmic origin has been a foundational pillar of modern science. The Big Bang Theory posits a single, immense event that gave rise to all of time, space, and matter. This framework provided a cosmic clock, a starting point that allowed us to ground our existence in a timeline we could measure, analyze, and model. It transformed a question once reserved for philosophy into a subject of scientific inquiry. Yet, the further the Webb telescope peers into space and time, the more it reveals a universe that does not look newly formed. Instead of witnessing the chaotic assembly of nascent galaxies, we're observing structures that are already well established, stars already enriched with heavy elements, and supermassive black holes already securely anchored at galactic centers. This does not look like the dawn of creation. It looks more like a process already in progress. In the realm of classical physics, the notion of a beginning establishes a boundary, a point where our established laws of nature cease to apply. The Big Bang singularity represents that very limit, a state of infinite density and temperature, with no explanation for what came before it. Time begins at zero, and there is no prior state. This, however, is not a complete scientific explanation. It is an acknowledgement of our ignorance, elegantly expressed in the language of mathematics. Alternative cosmological models, once relegated to the periphery, are now stepping into the scientific mainstream. Some cosmologists propose that the Big Bang was not a true beginning, but rather a phase transition, analogous to water freezing into ice. In this view, the universe may have emerged from a preceding state that we cannot yet observe, a state where quantum fields or higher dimensions existed in a fundamentally different configuration. Others theorize that the universe is eternal and never had a beginning, instead cycling through phases of expansion, contraction, and rebirth, never truly starting or stopping. Furthermore, a growing body of research in quantum gravity hints that time and space themselves might be emergent properties rather than fundamental components of reality. If this is true, the very concept of a beginning loses its meaning. It would be akin to asking when the surface of a lake began, while completely ignoring the underlying molecules from which that surface emerges. What propels these new ideas is not merely theoretical speculation, but observational evidence that challenges the standard Big Bang model. The galaxies observed by the James Webb Telescope are too developed, too massive, and too chemically mature for a universe supposedly in its infancy. The large-scale filaments of the cosmic web seem too orderly and defined. The stars appear far too seasoned for their supposed cosmic age. These findings do not just strain the accepted timeline, they suggest the timeline itself may be incomplete. But what would it signify for the cosmos to have no origin? It could imply that the universe is a perpetual engine, endlessly transforming its state without a definitive start. It might mean that our linear perception of time is a local illusion, and that reality as a whole does not adhere to a sequential narrative. Some of the more radical theories even propose a static block universe, where past, present, and future all exist simultaneously, and our sense of a beginning is merely a consequence of our limited perspective. The possibility of a universe without an origin revitalizes a timeless philosophical debate. Is the concept of creation a necessity? Is existence itself a product of causality? Or are we like fish in the sea, unable to perceive the ocean that surrounds us, compelled to believe in beginnings and endings, simply because that is how our minds are structured to process reality? This is not to say the Big Bang Theory is obsolete. It remains our most robust model for explaining many key features of the universe, including the cosmic microwave background, the expansion of space, and the abundance of light elements. This makes us wonder, is the Big Bang the ultimate beginning, or is it merely the beginning of our observable horizon? Ancient philosophers once imagined a timeless, perfect, and unchanging cosmos. Then came the Big Bang, which introduced the concept of a cosmic birth. Now, perhaps, we are returning to a similar idea. It is possible the universe never began. It may simply have always been. This forces us to rethink space-time itself and ask if our fundamental model of reality is broken. For over a century, our understanding has been shaped by Einstein's model of space-time. It depicts a four-dimensional fabric where mass tells space how to curve, space tells matter how to move, and time progresses steadily forward like a universal metronome. This model has been remarkably successful. It successfully predicted the existence of phenomena like black holes. Einstein's theories predicted the existence of gravitational waves and have since helped us create maps of entire galaxies, develop models for celestial paths, and even produce highly accurate guidance systems for spacecraft journeying through our solar system. Now, however, as the James Webb Space Telescope opens our view to the most remote corners of the cosmos, a more fundamental and disquieting question is coming into focus. What if space-time itself is merely an illusion? The more we observe, the more the universe appears to defy the very geometry we believed it inhabited. From galaxies that seem to form faster than space-time should allow, to stars that reach maturity before time could have granted them permission, we are witnessing cosmic behaviors that do not neatly align with our existing models. At the heart of this mounting tension lies a radical notion emerging from the world of quantum physics. Space and time might not be fundamental at all. In this view, what we perceive as space and time could be emergent phenomena arising from a deeper layer of reality, in the same way temperature emerges from the collective motion of molecules or a hologram forms from patterns of interference. It may be that time does not flow and space does not stretch. Instead, both could be coarse-grained perceptions, byproducts of something for which we do not yet possess the language to describe. This is far more than philosophical speculation. It is rooted in concrete theories such as causal set theory, emergent gravity models, and loop quantum gravity. These alternative ways of seeing the universe suggest that space-time is composed of smaller, more basic components, like tiny bits of quantum information that are linked together across a more foundational layer. And when the James Webb Telescope reveals a cosmos that behaves as if structure came before distance or memory existed before age, it compels us to ask if we are truly seeing space and time, or just discovering flaws in their underlying code. This even brings into question our most basic cosmic measurements. Redshift, which is the primary tool we use to determine how far away an object is, relies on the principle that space expands over time. But if that stretching is not real, or if it is not constant, then our entire understanding of the universe's scale could be flawed. It is conceivable that galaxies we believe are 13 billion light-years distant are actually much closer than we think. They might also exist somewhere else entirely, not in space in the conventional sense. Consider the phenomenon of entanglement, a quantum effect where particles separated by light years can act as if they are side by side. Some physicists propose this is not just a strange quirk of the quantum world, but a hint that distance itself is a kind of illusion. This would mean that two points can be intimately close in a deeper, information-based reality, even if they appear far apart in ours. If that is the case, then space may be relational instead of absolute, and the structure of the universe may be determined more by connectivity than by coordinates. Time fares no better under this scrutiny. In classical physics, time is absolute. In relativity, it is elastic, dilated by gravity and velocity. But in quantum physics, time is almost an afterthought. It is not a fundamental variable, but a parameter imposed by the observer. In some formulations of quantum gravity, time does not even exist. Things simply are, and what we refer to as change or causality is a type of narrative we impose on a timeless web of relationships. If Webb's observations continue to show galaxies acting as if time began before it should have, or as if space was organized before it could have evolved, we might have to consider a universe that is not just old, fast, or strange. We might need to envision a universe that does not use space-time at all. The catch is that we may already be witnessing the cracks in our current model. Interest is growing in the holographic principle, which suggests that all the information in the universe might be stored on a flat surface. Quantum entanglement, black holes, and even dark energy may all be signs that we are living in a projected world where space-time is just a construct and information is the true currency of the universe. This brings us to the intersection of quantum gravity and the early universe. We have known about gravity longer than any other force in nature. Newton described it with apples and orbits, and Einstein transformed it with the concept of space-time curves. Gravity holds galaxies together. It is the architect of black holes, and it directs the dance of planets and stars. But despite its immense power, gravity remains a strange outlier in the world of science. Unlike the quantum force's electromagnetism, the strong force and the weak force, gravity resists unification. It does not play well by the rules of the quantum realm, where uncertainty, entanglement, and probabilities reign supreme. Nowhere is this mismatch more urgent than in the moments just after the Big Bang, or whatever primal event our universe emerged from. The James Webb Telescope may not be able to detect quantum gravity directly, but its discoveries are now pushing scientists to revisit this elusive frontier. The telescope's observations of galaxies forming too early, stars becoming enriched too quickly, and structures appearing without the expected scaffolding of time and space all suggest that something deeper, a more fundamental law of nature, may be at work, something that only a theory of quantum gravity can explain. At its core, this is the effort to reconcile general relativity with quantum mechanics, to describe how gravity operates when things are extremely small and incredibly energetic, such as in the first instant of the universe or inside black holes. But traditional physics breaks down in these extremes. General relativity predicts a smooth space-time, while quantum mechanics predicts fluctuations, uncertainty, and discrete bits of information. When you combine the two, you get mathematical chaos, infinities, nonsensical results, and models that implode. To fix this, builders of these theories are creating brand new systems from scratch. String theory proposes that particles are not points, but rather strings that vibrate and exist in up to 11 dimensions. If the extra dimensions are hidden or curled up together, these strings can bring together all the known forces, including gravity. String theory even accounts for branes, which are higher dimensional walls that could hold entire worlds. This is where concepts like the multiverse and a cyclical cosmos can grow. Loop quantum gravity, or LQG, on the other hand, takes a different direction. It suggests space is broken up into separate pieces, like dots on a computer screen. LQG posits that space is not a single, continuous block, but a grainy mesh made of tiny loops of quantum information. In this network-like structure, time is no longer a smooth flow. It changes as the network itself evolves. One of its most important implications is that the Big Bang was not the start of everything, but was instead a quantum bounce, a transition from a universe that was squeezed into a small, non-singular state. These are not just esoteric mathematical games. The James Webb Space Telescope may be guiding us toward the ability to conduct real tests on these profound concepts. As one example, if space and time are themselves products of quantum processes, then the infant universe should bear distinct quantum fingerprints. These imprints might appear as subtle variations from smoothness, the formation of unexpected structures, or even peculiar ways that light travels across the cosmos. Certain discoveries from Webb, like galaxies that seem to disregard the established rules for how quickly structures can form, could be these very hints. Even the universe's apparent uniformity, a characteristic long explained by the theory of inflation, might find an alternative origin in quantum gravity. In some theoretical frameworks, quantum entanglement across a pre-space-time state could explain the deep coherence observed between distant cosmic regions. These models suggest that our familiar notion of causality may not have been applicable during that first epoch. Everything could have been interconnected in a pre-geometric state where the concept of distance had not yet come into being. One of the most significant implications is the idea that information is more fundamental than matter or energy, and that patterns of quantum entanglement might actually define the very fabric of space-time. From this vantage point, the universe is not an object expanding through pre-existing space. It is more like a computer, an immense quantum network that translates information into experience. Therefore, when the James Webb Telescope peers into the distant past and discovers fully formed galaxies or black holes far too close to the beginning of everything, it may not be an error in the instrument or the data. In this realm, space, time, and gravity are not the fundamental rules but are instead emergent effects. This could be a direct glimpse into the quantum origins of our reality. The long-sought holy grail of physics has been a theory of everything, a single formula to unify the cosmos. But perhaps what is needed now is not a single theory, but a complete paradigm shift. This would be a new way to perceive the universe not as a place governed by forces, but as a process unfolding from a quantum fog. It would be a reality where beginnings are illusions and gravity is not a cause but an echo. This brings us to the James Webb Telescope and the potential demise of the standard model of cosmology. This model, known as lambda CDM or lambda CDM for lambda cold dark matter, has for many years been the central framework of modern astronomy. According to this theory, the universe started with the Big Bang. It also outlines the initial period of inflation, the formation of the cosmic microwave background, the distribution of galaxies, and the mysterious dark ingredients, dark matter and dark energy, that sculpt the cosmos. It is an elegant model with predictive power, one that has successfully passed numerous observational tests. The standard model, however, was always a best-fit theory, a composite of observations carefully assembled into a coherent narrative. It rested on bold assumptions that space-time is smooth and homogeneous on vast scales, that gravity dictates the formation of structure, and that redshift reliably measures distance and age. Yet it was also burdened with deep mysteries. What exactly is dark matter? Why is dark energy causing the universe's expansion to accelerate? What occurred before inflation? The model worked, but only by requiring acceptance of things we could not see, define, or fully test. Now, the telescope has identified galaxies that are too mature, too massive, and too structured to exist at such early cosmic epochs. Based on the standard model, the early universe was a chaotic plasma of particles that slowly cooled and clustered. It should have taken hundreds of millions, if not billions, of years for galaxies to achieve the size and structure Webb is now detecting, just 200 to 300 million years after the supposed beginning. This is a significant discrepancy. It is not a minor adjustment, but a fundamental break. This implies that the model's core ideas about time, matter, and energy might be incorrect. The established timeline appears to be wrong. The cosmic structures seem to have been completed ahead of schedule. It now seems that the equations that brought us to this point were never equipped to describe this corner of reality. Even more concerning is the growing tension in cosmological measurements. The Hubble constant, which measures the rate of cosmic expansion, yields different values depending on whether it is derived from the early universe, via the CMB, or from nearby galaxies, which Webb is now observing. This disparity between the measurements is growing, not shrinking, raising the unsettling possibility that we are not fully grasping the universe we are measuring. these issues are not merely observational puzzles, they penetrate to the conceptual core of the Standard Model. If galaxies form faster, if time behaves differently, and if redshift is not a dependable clock, then the foundations of LCDM begin to shake, and scientists are taking notice. Some researchers now suggest that Webb's data may require an entirely new theory of the universe. This would be a theory that does not just patch the old one, but rebuilds it from the ground up. That could entail a departure from a model where dark matter and general relativity are the primary governing laws, moving toward one where quantum information, emergent space-time, or unknown physical principles take center stage. Others propose that we might need to re-examine old data in a new light. It is possible that our predictions themselves were flawed, now that Webb is revealing a cosmos that does not conform to our expectations. The cosmic microwave background has long been considered our clearest snapshot of the early universe, but perhaps we have been misinterpreting what it shows us. It is conceivable that dark matter is not a particle but a field, or a manifestation of unexplained forces. Maybe dark energy is not actively expanding the universe. It is possible that space itself is transforming in a way we have not yet considered. This is not a rejection of science. It is science functioning as it is meant to, by confronting the unknown and refusing to turn away. The Standard Model served us well. It guided us to the moon and far beyond. But models are not meant to be eternal. They are tools, not absolute truths. And when the tools no longer match the data, it is time to invent new ones. The scientific community's reaction to this has been a subject of great interest. When the James Webb Space Telescope returned its first images to Earth, most scientists expected some shocks, such as sharper images, deeper insights, and perhaps some adjustments to the cosmic timeline. What they did not anticipate was an accumulating number of discoveries that would challenge modern cosmology at its very foundations. As the initial findings arrived, galaxies too massive to be possible, structured clusters that appeared too soon after the Big Bang, and black holes that grew faster than models predicted, the response from scientists was mixed, sometimes nervous, and often one of deep reflection. In the halls of research institutions and the pages of scientific journals, one thing became abundantly clear. Webb was doing more than just revealing the universe. The new observations were revealing the very limits of our understanding, and many cosmologists reacted with a blend of awe and disbelief. For some, the findings were nothing short of exhilarating. After decades of working within the established constraints of LCDM, they perceived Webb's anomalies as a clear permission to rethink, to question assumptions that had perhaps grown too comfortable. One astrophysicist suggested that they had been given the opportunity to rewrite cosmology from its foundations, an opportunity it would be foolish to pass up. Others, however, responded with caution and even a degree of resistance. The Standard Model, they argued, has earned its central place through decades of predictive success. It elegantly explains the cosmic background radiation, the vast structures of the universe, and the abundance of light elements. For these scientists, anomalies are not a reason to abandon the model, but rather a prompt to refine it. It is possible star formation in the early universe was more efficient than we had imagined. Perhaps dark matter exerted a greater influence, or the process of inflation worked differently. They see this not as a revolution, but as an evolution, a series of adjustments, not a complete teardown. And in truth, science is not typically built upon dramatic overthrows. Its progress is marked by slow, methodical correction. Paradigm shifts tend to occur not in headlines, but quietly in footnotes, at conference talks, and through peer-reviewed debate. Still, a palpable tension exists just beneath the surface. Some researchers express a growing concern that the cosmological community has become too invested in its models, too unwilling to admit when the data no longer aligns. They point to historical parallels where entrenched thinking slowed progress, such as the resistance to heliocentrism, the rejection of quantum theory, and the initial dismissal of plate tectonics. A similar pattern, one theorist warned, could be emerging, where a model becomes dogma, and dogma is the enemy of discovery. This strain is most apparent in the way science is discussed in public. Headlines proclaiming that James Webb could rewrite cosmic history or that the Big Bang is under fire now appear in articles that once praised the Standard Model. On social media, astrophysicists debate redshift readings and the early stages of galaxy creation with an intensity that rivals philosophers arguing the nature of time. Some embrace the chaotic energy of it all, while others call for moderation. The discourse is widespread and often remarkably honest. A significant part of the disagreement is rooted in the fact that Webb's data is so new. We are in an unprecedented situation, seeing parts of the universe never before witnessed, and with a level of detail from ultra-deep infrared images once thought impossible. It is not yet known if the strange phenomena we are seeing are real or if we are simply misunderstanding them. The possibility of calibration mistakes, unknown observational biases, and reading errors still remains. And yet, multiple teams using independent methods and instruments are beginning to verify similar results. Early galaxies that break formation models, redshifted light that raises uncomfortable questions, and black holes that seem to skip evolutionary steps. As these patterns harden into confirmed facts, a new generation of physicists is stepping forward. These are researchers less wedded to the old ways, more comfortable navigating the unknown. For them, Webb's revelations do not represent a crisis. They are an invitation to explore new ideas, to resurrect discarded theories, and to build models that reflect a universe that may be stranger, older, or deeper than we dared to dream. Some are taking another look at unconventional ideas like tired light, plasma cosmology, and bouncing universes. Others are working on quantum gravity models that do away with the singularity, instead describing space-time as a probabilistic network of entanglement and information. What was once pushed to the margins is now getting attention, not as a solution, but as a fair question. However, the most honest words may be that we simply do not know, because science is not ultimately about protecting what we know. It is about having the courage and curiosity to confront what we do not. In that task of showing us what doesn't fit, the James Webb Telescope is more capable than any tool in history. On the other side are the Big Bang loyalists, defending the standard model. To them, the Big Bang is not just a theory. It is a battle-tested framework that has survived one of the most demanding gauntlets in all of science: prediction, observation, and repeatability. The standard model successfully predicted the cosmic microwave background long before it was discovered. It explained the abundance of light elements in the early universe. It accounts for the expansion of space, the formation of large-scale structure, and the growth of cosmic voids. These are not small victories. They are monumental achievements that earned the model its throne. So when James Webb unveils galaxies that appear more mature than expected, or black holes seemingly form too quickly, loyalists do not panic. They analyze. They adjust parameters. They explore the margins of existing theories. One common defense is that Webb is showing us not the average galaxy at a given redshift, but the exceptional ones, the statistical outliers that formed earlier or evolved faster than the norm. Another explanation centers on selection bias. Perhaps we are currently seeing only the brightest, densest galaxies, because those are the easiest to detect with infrared instruments. As Webb continues to collect more data, including fainter, more typical galaxies, the apparent anomaly might dissolve into a more familiar cosmic pattern. Then there is the question of dust and lensing. Material between the stars and gravitational effects could be changing how old and bright these galaxies look. It is possible that these effects make them appear older, bigger, or more organized than they really are. Some supporters say that what we're seeing might not be a problem with the standard model, but an incorrect reading of the signals. One more point is based on practicality. Even with its problems, the standard model is still the best way to study and understand the universe. It does not have to be thrown away completely. It can be changed. For example, new types of dark matter, better inflationary models, or early explosion processes could be added. This way of thinking is similar to how Newtonian physics gave way to relativity, not by rejecting it, but by incorporating it into a bigger picture. Loyalists also point to the danger of what they call anomaly hunting, the tendency to latch on to unexplained data points and build entire alternative frameworks around them. Anomalies, they argue, are not new. The history of cosmology is filled with anomalies, and most have eventually found their place within the prevailing model once more complete data arrived. As one cosmologist wrote, "Science does not advance on excitement alone, but on moments when consistency breaks down across the board. That critical point has not yet been reached. This is a perfectly valid stance. True paradigm shifts in science are rare, justified only when no amount of adjustment can reconcile an old model with new observations. As of now, many of the Webb telescope's findings, while startling, have not crossed this threshold. And in the eyes of those who support the Big Bang model, the burden of proof lies with its challengers. Yet what is perhaps most admirable about these loyalists is not a rigid adherence to theory, but a deep commitment to rigor. The scientific method itself demands skepticism, not just of new ideas, but of our own assumptions. It is easy to be seduced by the prospect of revolution. It is far harder to hold the line until the evidence is airtight. Even so, many proponents are becoming more aware that the plan needs to change. There is little disagreement that what Webb has found is strange. A broad consensus is forming that something new is on the horizon, whether it is new information about how stars form, a new way to look at redshift, or the first signs of a crack in a theory once thought to be unbreakable. The ultimate commitment, then, is not to a theory but to the method itself. The Big Bang remains the default explanation because it works so well. But if the day comes when it no longer does, when the evidence calls for a different story, even its most devoted supporters know what must be done. In response, radical new models are being proposed. Science does not fall apart when a theory's foundations begin to shake. Instead, it evolves. Since the James Webb discoveries seem to challenge our fundamental understanding of the cosmos, a quiet but rising revolution has taken shape in theoretical physics. More cosmologists are looking to bold new models of the universe that rewrite the rules from the very beginning. These concepts were once on the fringe because they contradicted the established cosmic history. Among the most talked about is the Big Bounce model. Rather than a universe born from a singular, explosive beginning, the Big Bounce proposes that our cosmos is the latest in a cyclical series of universes, expanding, collapsing, and rebounding over and over through infinite time. In this view, the ultra-early galaxies seen by Webb are not premature at all. They are leftovers, remnants from a prior cycle's end, where gravity compressed the universe until it rebounded into a fresh expansion. There is no beginning, only transformation. Roger Penrose, a Nobel Prize winner and one of modern physics' most recognized minds, developed a concept known as conformal cyclic cosmology, or CCC. This model says that the conditions at the start of a new universe are exactly the same as those at the end of an old one. This is because expansion stretches the old universe so far that everything breaks down into massless particles. There is no single event, as one eon ends and the next one begins. Webb's finding of strange order in the early universe could be seen as information from a different time in the universe leaking through. Emergent space-time models are also getting more and more attention. In these frameworks, space and time are not basic at all, but instead come from quantum information structures. These ideas suggest that the universe works like a computer program, where entanglement and the flow of information cause things like distance, time, and gravity to emerge. The issue is not that the timeline is broken, but that our very sense of time is wrong. Some forms of this theory say that the early universe looked fully formed because space-time came into being all at once, like starting up a game. In the more speculative corners, we find theories like plasma cosmology, which rejects expansion entirely. It proposes that the universe is an immense, stable structure shaped by electromagnetic forces, not gravity and dark energy. In this view, redshift is not due to expansion, but to energy loss through interaction with the intergalactic medium, a revival of the tired light hypothesis. While controversial and often dismissed by mainstream astrophysics, plasma cosmology has gained renewed interest due to Webb's challenges to traditional expansion metrics. Then there is the model of a holographic universe. This idea is based on string theory and black hole physics, and it says that everything we see as three-dimensional is actually information stored on a two-dimensional boundary. The world is not growing bigger in space. Instead, it is moving forward from a surface of quantum data. In this model, it is not a bug for early galaxies to form in fully grown states. It is how information unpacks across the hologram screen. Some very extreme models even go after the holy principles of nature. A number of scientists are looking into whether things like the speed of light or the gravitational constant may have changed over time, which would have had a small effect on how the universe formed in the beginning. In that case, things we think of as strange could be proof that the cosmos used to follow a different set of rules when it was first formed. Still others believe we may be living in a multiverse, where our corner of reality simply reflects unusual initial conditions. What seems improbable from our perspective might be common somewhere else. In these models, early galaxies, strange redshift behavior, and mature stars are features of a localized cosmic bubble, not failures of a universal law. These ideas, though different, share the same spirit: cosmic humility, the understanding that the universe does not have to work the way we want it to, and that sometimes we need to see things in a different light to find the truth. Radical models do, of course, come with risks. They are usually less beautiful, harder to test, and quickly thrown out as theoretical. But they also make the discussion bigger. They make it possible to do new math, make new discoveries, and think about old problems in new ways. This has profound philosophical implications. What if the universe had no beginning? Since the beginning of time, people have looked up at the sky and asked, where did all this come from? Every culture has its own story about how the universe came to be. From gods making the world to machines calculating space and time, there is still a story behind modern science. Even though it is based on data, it tells of a world that was born, grew, and changed. And now we are here to ask about it. This is not just a scientific dilemma. It is a philosophical upheaval. A universe with no beginning presents a profound challenge to our most basic frameworks for causality, purpose, and meaning. We are, at our core, creatures of narrative. Our brains seem wired to process reality through arcs that have distinct starts, middles, and ends. Even our personal lives are framed by this structure: birth, life, and death. So when the field of cosmology begins to threaten the very concept of a birth for the universe itself, the issue becomes not just one of physics, but of existence. At the heart of the Standard Model lies a theoretical moment called T=0, the singularity, which is held to be the origin of all space and time. But if the discoveries from the Webb telescope suggest that structure, matter, and even mature galaxies were already in place before what should have been the opening scene, then our very concept of a starting line begins to dissolve. The philosophical effects that ripple from this are considerable. One of the most significant is how it alters the idea of a first cause, a concept that has been a cornerstone in philosophy and religion for millennia. The notion that everything must have a beginning underpins many arguments for the existence of a creator, including Aristotle's unmoved mover and the standard cosmological argument. That entire chain of logic is broken if the universe has always been here. There would have been no first result, and therefore no need for a prime cause. This could either threaten or liberate theological thinking. Some traditions might resist this idea, clinging to a singular creation event as proof of divine action. Others, however, could embrace a more timeless and omnipresent concept of divinity, one not confined to a beginning but instead embedded within the eternity of existence itself. Then there is the question of meaning. In a universe with a definite beginning, we can imagine a direction, a purpose, or trajectory that commences with creation and progresses toward complexity, life, and perhaps even consciousness. But if there is no beginning, then perhaps there is also no intended direction. We are not a culmination. We are simply a moment in an infinite chain of cosmic fluctuation. This might feel bleak, but it can also be profoundly liberating. It suggests that the world does not have a built-in meaning for us to find, but that meaning is something we ourselves must make. In a universe that will never end, our purpose is not to follow a plot that has already been written. It is to write our own meaning over and over against the universe's vast indifference. There is also the matter of time itself. Philosophers such as Kant argued that time is not something that exists externally, but rather a structure that our minds create to make sense of reality. If the world does not have a start, then time itself might not be as fundamental as we believe. Some scientists already propose that time is an emergent quality, one that arises from the intertwined behavior of quantum systems or thermodynamic patterns. From this point of view, the beginning is not a real event, but simply a point where our current understanding ends. This brings us to what may be the most disquieting implication. Our questions may not be the right ones. If the world has always existed, then asking when it started might be as illogical as asking what is north of the North Pole. The question itself is a misuse of language and logic. Perhaps our deep desire to know where we came from is merely a product of living within time, and not a reflection of how the universe is truly put together. With a sense of deep respect, not chaos, the James Webb Telescope is more than just a telescope. It is also a mirror. It shows us both the early light of the universe and the inherent limits of what people can comprehend. It reveals that even the most important ideas we hold dear, like starts, causes, and narrative arcs, may just be small-town comforts. Webb, however, is not the end of the story. Even though its findings have transformed our thinking, a fleet of next-generation projects is preparing to go even deeper, wider, and into stranger territory than ever before. This is the beginning of a new era in science. Many are looking forward to NASA's Nancy Grace Roman Space Telescope, which is set to launch later this decade. It is often said that Roman will have a field of view 100 times larger than Hubble's, with the same level of sharpness, a combination that will make it perfect for observing huge areas of the sky in great detail. While Webb looks very deeply and narrowly into the past, Roman, on the other hand, will map the structure of the universe on immense scales, keeping track of how galaxies group together and how dark energy affects the accelerating expansion of the cosmos. Where Webb points out the weirdness, Roman will measure how strange it truly is, helping to decide if such oddities are random events or systemic flaws in our understanding. On the ground, the Vera C. Rubin Observatory in Chile, scheduled to begin full operation soon, will conduct the Legacy Survey of Space and Time, or LSST. This ambitious 10-year program will catalogue billions of galaxies, track transient events like supernovae and asteroids, and create what is essentially a motion picture of the dynamic universe. Rubin's strength is not depth, it is motion and pattern, giving us time-based insights to match Webb's static snapshots. If the early universe was more chaotic, faster evolving, or more discontinuous than we think, Rubin will be the observatory to catch those subtle temporal fingerprints. Meanwhile, Europe's Euclid mission, launched by ESA, is already scanning vast regions of the cosmos to study the mysterious fabric of dark energy and dark matter. While it may not match Webb's infrared sensitivity, Euclid complements it by focusing on gravitational lensing, how light from distant galaxies is warped by massive structures. This will help scientists test whether general relativity itself breaks down at cosmic distances, potentially replacing Einstein's theory with something more exotic. The Extremely Large Telescope, or ELT, is a huge structure being built on the ground in the Atacama Desert. The ELT will be able to directly view the first stars and exoplanets, thanks to its 9-meter mirror, which is the biggest of its kind. This will allow for spectroscopy of ancient galaxies that has never been done before. Unlike space telescopes, it can be improved and kept up to date, which makes it a long-term watchdog for finding the quantum and chemical signatures of cosmic structures that do not fit with current models. In the more distant future, NASA is working on LUVOIR, which stands for the Large Ultraviolet Optical Infrared Surveyor. This is a concept for a project that will be much more powerful than Webb. LUVOIR is designed to look into everything from how life might begin on faraway exoplanets to the most mysterious objects in space that are hiding in plain sight. If it were to be launched, LUVOIR would be the most powerful all-purpose space telescope ever made. It could also be the best tool we have to find out if the universe had a beginning at all. Beyond the instruments of today, even more extraordinary concepts are taking shape on the horizon. Future endeavors, such as the Laser Interferometer Space Antenna, or LISA, are designed to perceive gravitational waves directly from space. This will effectively open an entirely new sensory channel for observing the universe, allowing us to listen to the mergers of black holes and perhaps even the fundamental vibrations of reality itself. Gravitational waves carry information that light cannot, potentially revealing ripples from cosmic events that occurred before the universe was transparent. As the lines separating astrophysics, quantum theory, and cosmology continue to dissolve, the observatories of the future may bear little resemblance to conventional telescopes. One can imagine vast swarms of coordinated satellites creating immense artificial interferometers across space. It is also possible they will employ quantum sensors to register the most subtle shifts in the curvature of space-time. Other missions might seek to analyze the cosmic neutrino background or search for relic gravitational radiation from theoretical states that may have existed before the Big Bang. This brings us to a crucial distinction between media narratives and scientific reality, particularly in the misreporting of the Big Bang's supposed demise. While nuance is essential for scientific progress, the internet's economy often rewards certainty, conflict, and clickable headlines. The James Webb Space Telescope delivered data that was genuinely perplexing, revealing galaxies that appeared too massive, too mature, and too organized for their calculated distance and age based on redshift. These findings are compelling us to reconsider our models of the cosmos, which is a healthy and necessary process. However, they do not invalidate the Big Bang any more than the earliest airplane accidents negated the concept of flight. Many of the experts featured in popular articles found their words taken out of context, their cautious statements misinterpreted, or their significance inflated. For a professional cosmologist, dramatic declarations like "the universe is older than we thought" or "the Big Bang is in crisis" require immense care and qualification. The Big Bang itself is not a singular, fragile idea about a moment in time. It represents a comprehensive model, a framework built upon decades of rigorously tested observations. These foundational pillars include the continuous expansion of space, the faint, persistent glow of the cosmic microwave background, and the specific ratios of light elements forged in the universe's infancy. These core observations remain undisputed. The James Webb Telescope has not overturned them. What it has successfully done is stimulate a vigorous new debate about the period immediately following the initial expansion and the mechanics of how the very first structures came into being. In the media landscape, however, these subtle questions about early cosmic structure formation were quickly transformed into bold proclamations that the Big Bang theory was finished. This reflects a recurring pattern that has long been a challenge for science communication. A single puzzling data point is often presented as definitive proof that our entire body of knowledge is incorrect. A carefully worded, tentative statement from a researcher can become a sensationalized headline. The methodical process of science, which relies on gradual refinement, extensive peer review, and cautious interpretation, is often overshadowed by the demand for spectacle. This disconnect carries significant real-world implications. It can foster public misunderstanding, create polarization in public discourse, and sow seeds of distrust in the scientific endeavor. For a casual news consumer, the perceived oscillation between headlines claiming science proves everything and science is completely wrong can create a false impression. It can make the scientific process seem like arbitrary guesswork, a fragile enterprise that changes its mind with every new photograph. The deeper reality is that science is, by its very nature, resilient. Its theories are not treated as sacred texts, but as practical tools. When these tools no longer perfectly match the observations, they are sharpened, recalibrated, or sometimes replaced with better ones. What the James Webb Telescope is accomplishing is precisely the function of a great scientific instrument. It is pushing us beyond our comfort zones, revealing our blind spots, and helping us formulate sharper, more insightful questions. It is vital to understand that most scientists are energized by these anomalies. Their excitement stems not from a desire to discard the Big Bang, but from the opportunity to explore fresh intellectual tensions. For many years, the field of cosmology had perhaps settled into a period of intellectual complacency. The Standard Model was remarkably successful at explaining most observations, but Webb has cracked the cosmic view wide open once more. With that comes the tantalizing possibility that a deeper layer of physics is waiting to be discovered. The public, however, deserves a more nuanced narrative than a simplistic fight between Big Bang is dead and Big Bang is alive. They deserve to understand that this is not a war, but a conversation. It is a dialogue certainly filled with disagreement, but it is also defined by rigor, deep collaboration, and profound humility. The scientific community is not a collection of heroes and villains. It is composed of dedicated individuals, all trying to comprehend something far larger than any single person can grasp alone. Within this community, There are researchers actively working to defend and refine the standard model. There are others who are proposing radical new alternatives. And there is a large group in the middle asking whether the data itself might be misleading us, questioning if factors like cosmic dust, gravitational lensing, or our interpretation of redshift are introducing errors. What unites all of them is a shared foundation of curiosity and a commitment to evidence. We may be witnessing the dawn of a new golden age of cosmology. The question arises whether we are at the beginning of a truly transformative era. The last time physics underwent such a fundamental shift was in the mid-20th century. It was a period marked by the discovery of the cosmic microwave background and Hubble's confirmation that the universe was expanding. In that era, the Big Bang model triumphed over the competing steady-state theory. It was a time when everything seemed new, unbroken, and brimming with potential. That was the first golden age, the moment we transitioned from simply marveling at the cosmos to being able to systematically study it. What makes this current era golden is not just the incredible technology, although that is a powerful enabler. It is the renewed willingness to reimagine our most basic assumptions. For several decades, the standard model of cosmology provided a reliable and comfortable intellectual harbor. Now, however, scientists are once again embracing the winds of uncertainty. They are re-examining long-forgotten theories and proposing bold new models where information, not just matter, might be the universe's fundamental component. They are seriously asking if galaxies could have formed before our current physics says they should have. Instead of dismissing anomalies, they are actively pursuing them. A new generation of missions, including the Nancy Grace Roman Space Telescope, the Vera-C, Rubin Observatory, and the Euclid Probe, are preparing to gather data on an unprecedented scale. These powerful instruments will map billions of galaxies, meticulously track cosmic acceleration, and investigate dark energy in ways that will either powerfully reinforce our current understanding or completely redefine it. This is no longer a series of solo expeditions. It is a coordinated fleet setting sail into the unknown. Simultaneously, ground-based observatories like the Extremely Large Telescope and theoretical explorations into quantum gravity and emergent spacetime are extending our reach from both observational and conceptual frontiers. Together, all these efforts create an interconnected network of insight. Each new discovery serves to cross-validate, challenge, or reframe the others. The result is a feedback loop of discovery that feels almost exponential in its growth. Yet, the expansion of scientific knowledge alone is not what makes this period truly golden. The defining characteristic is the spirit of collaboration across disciplines, across nations, and even across different systems of thought. Philosophers are re-engaging in vital conversations about the nature of scientific inquiry. Mathematicians are working to formulate new languages to describe the universe. Artificial intelligence and machine learning are accelerating our ability to find subtle patterns within vast cosmic datasets. And remarkably, amateur scientists are discovering supernovae and exoplanets from their own backyards, using tools of a quality once unimaginable outside of professional institutions. This moment feels different, defined not by established fact, but by profound possibility. What is now on the table seems more vital than our models, our math, or even our instruments. It revives timeless human questions about truth, our purpose, and whether our world is the only one. In place of old convictions, a growing humility is taking root. Perhaps the true sign of a golden age is not in possessing answers, but in the ability to ask better questions, inquiries a previous generation would not have dared to pose. Consider what this really means. Right now, our most basic ideas about the universe are being tested not by stories, but by direct observation. Every new image is a test of how we fit into the cosmos. A theory ends, and wonder begins. At the precise moment, scientists must defend what works while accepting what does not. The Big Bang Theory has been our compass for nearly a century, giving us a beginning, a framework, and a way to understand our place. For generations, it lit the path forward. From Einstein's equations to Hubble's redshift, from microwave background maps to particle accelerators, it taught us to think on a cosmic scale, to imagine time as a thread and space as a fabric. This could be the start of something stronger, because failure is not when an idea stops working. It is the return of awe. It is the moment we realize the map no longer matches the terrain, and instead of fear, we feel an openness to what might be possible. This potential only emerges when we set down old tools to look for new ones, and we are in such a moment now. We are confronting the idea that space may not be fundamental in the way we imagine, that time may not tick universally across the cosmos. We face evidence that the early universe may have skipped steps our physics deems mandatory, that galaxies formed before they were allowed to, their central black holes too large, too soon, too perfect. In the past, such anomalies would have sparked quiet debate in academic circles. Today, they are part of a global conversation on computers, in classrooms, on podcasts, and on TikToks. The puzzle is no longer confined to labs. It belongs to all of us. The real progress is not in having all the answers, but in being willing to stand at the edge of our knowledge and admit we might have been wrong. Space may not be what we thought. The beginning may not have been a beginning at all. We might need a new language, one made of quantum threads, emergent rules, or something we have not yet conceived. The James Webb Space Telescope is more than just an assembly of gold-plated mirrors and electronics. It is a mirror for our own understanding, showing us the cosmos as it truly is, not as we think it should be, messy, beautiful, and unfinished. And it is through this new view that all of us who think, doubt, and dream must now walk. The next phase may not be a sudden breakthrough. It could be a period of stress, ambiguity, and argument, with years of false starts and failed models. But every golden age begins with this kind of disruption, with the ground we thought was solid breaking apart. Upon that broken ground, we will begin to build again. The James Webb Space Telescope has not just given us stunning pictures, it has revealed a profound gap in our oldest story about the universe. Whether the Big Bang model collapses or is transformed, one thing is certain. We are on the verge of a new era in cosmology, where questioning leads to discovery and mystery leads to deeper certainty. If this journey has changed how you think about the universe, do not stop now. We invite you to join us as we go deeper into the questions that make life possible, because as the world changes, so do we.